How do planets lose their stars and drift alone through the dark? What clues in starlight reveal these invisible wanderers? Could rogue planets outnumber the stars themselves? Imagine drifting silently in an endless ocean of midnight. There are no boundaries here, only the vast expanse of space stretching in every direction beyond imagination. The darkness is profound, so quiet that even a whisper of wind seems impossible. Under the canopy of stars, our senses tell us everything is still. Planets orbit their suns with familiar rhythms. But here beyond those gentle dances, there is only peaceful emptiness. In this silent sea between the stars, even time seems to stretch. The airless stillness is overwhelming, as though the cosmos itself held its breath. Beyond the golden glow of any sun, there are worlds that drift on their own. But here, at the very edge of our understanding, all of it is quiet and still, with only faint constellations in the distance to remind us of warmth and light. Our minds, used to life under sunlight, try to fill the void with imagination. In the deepest darkness of this cosmic ocean, faint hints of movement stir our curiosity. If the stars are islands of light, then perhaps there are lonely worlds adrift between them. A gentle stirring of wonder suggests that even in this vast silence, secrets await discovery. We might pause to consider how vast this void truly is. Even the nearest star is so far away that its light travels for years before it whispers to us. Between those distant suns are empty stretches measuring trillions of miles. It is in this colossal solitude that our story begins, pondering worlds that may wander alone, unseen by any light. Long before modern space travel, ancient observers gazed up at the night sky and wondered at its mysteries. Even then, faint whispers of a wild idea floated. Could there be worlds lonely and free, untethered from the glow of a parent star? For centuries, planets were envisioned only as companions circling suns. But some daring thoughts suggested that the cosmos might harbour drifters, planets without a home. Even our own solar system bears witness to chaos. Planets might wander if enormous forces arise. Some scientists speculated that in the chaos of star formation, newcomers could be flung free. If the early solar system was crowded and active, could Earth or Jupiter once have been at risk of being tossed into the dark? It was a question that pushed beyond imagination, but those whispers of possibility became first suspicions. These early suspicions were mere seeds. The thought lingered. If entire stars can drift beyond galaxies, why not planets? By the 20th century, as telescopes improved and theories expanded, this idea could not be completely ignored. It remained a fringe thought, but the notion of worlds without sun became one of those quiet questions in the scientific ether. It was only in the late 20th and early 21st century, as humanity detected planets orbiting distant suns, that astronomers dared to dream bigger. Observing one star after another, they realized we cannot see everything. If planets could orbit far-flung stars, maybe they could also wander astray. Every new discovery of exoplanets fueled curiosity. It was now conceivable that planets might also exist without a parent star, roaming dark corridors of space. For a long time, these notions were just that. Notions, fragile as starlight. Astronomers asked themselves, what would a lonely planet even look like? Since it gives off no light of its own, detection was impossible with their telescopes. And yet, the question refused to die. The idea of mysterious wanderers remained on the fringe, a whisper in the night of scientific imagination. Finding a rogue planet is like trying to see the invisible. Without the glow of a parent star, a drifting planet is wrapped in perpetual darkness. It doesn't shine in the night sky. It reflects nothing. Even if it produces a little heat internally, that warmth radiates weakly. To our telescopes, it looks like nothing more than a cold speck lost among the stars. If you imagined searching the pitch-black void for a silent traveler, you begin to understand the challenge. Without starlight to illuminate it, a rogue planet is very hard to spot. Our instruments rely on light, visible or invisible, to see distant objects. But in the cold dark, a free-floating world offers no signature. It is darker than the shadows, like a phantom drifting through the cosmos. Even our most sensitive cameras might pass by without noticing, unless something else betrays its presence. Most wandering planets grow cold and silent. A newborn world might still glow faintly in the infrared, a fading ember in the cold. But as millennia pass, even that glow dims. Eventually, a rogue planet would be nearly indistinguishable from empty space. Unlike stars or planets we know orbiting suns, these wanderers leave almost no trace. In the eyes of a telescope, they vanish into the black background of the universe. A final difficulty is that these planets roam unpredictably. A planet around a star stays in a fixed orbit that we can track, but a rogue's path is free. Without knowing where to point, astronomers must scan wide and pray for a lucky alignment. It is the ultimate hide and seek. To detect a planet without a star, astronomers must catch a fleeting sign or chance encounter. That elusive nature makes the search long and hard. Then came a glimmer of hope, in a way no one had expected. Over a century ago, Einstein showed that mass bends light like a lens. In principle, even a planet could briefly magnify a distant star's light as it drifts across our line of sight. For years, this was just theory, a delicate trick requiring perfect alignment. But if anyone could watch millions of stars for such rare alignments, maybe, just maybe, these invisible worlds could finally be seen. Astronomers began the hunt. Telescopes scanned rich fields of stars in the galactic bulge. Every night, cameras captured brilliant stars and dimming glows, tracking their brightness precisely. These international teams, named OGLE and MOA, among others, watched the Milky Way's heart endlessly. If a star's light grew brighter for a few hours or days, they would see it and know something interposed between us and that distant sun. This work paid off. Time after time they observed stars, softly brightening and dimming, according to Einstein's predictions. In most cases, the lensing came from whole stars, or planets, that still circled them. But then, something strange emerged. A handful of events were far too brief. A background star would suddenly flare, brighter than before, but only for a fleeting moment. It was as if the secretive lens vanished, almost as soon as it appeared. This is where the hunt got truly interesting. The unusual events, though rare, hinted at hidden, starless masses. With careful analysis, the astronomers concluded that these were likely planets unbound to any star, rogue planets. It was the first glimpse of them. In the blink of an eye, an entire world had announced itself and then disappeared back into the darkness. Under scrutiny, these strange events revealed a secret. The lenses were of planet mass, with no detectable star in tow. The conclusion sent a thrill through astronomy. For the first time, there was a tangible sign of the rogue planets that had long been imagined. A lonely world, by bending light, had briefly made its existence known before fading back into the cosmic sea. It was a stunning breakthrough, even if it came in whispers. These signals from the dark convinced more astronomers to listen for similar clues. Quiet, flying worlds had finally been glimpsed, if only for a moment. This discovery began to change our view. The galaxy might be full of hidden planets beyond anything we'd ever expected. Astronomers watched for years, and the strange signals kept arriving. A star in the background would suddenly flare, and then quickly dim, sometimes within a single night. These occurrences were unlike any known lensing by stars. Each time, meticulous analysis showed the lens must have been the size of a planet. Slowly, piece by piece, these flickers in the data formed a pattern. They were whispers of hidden, free-floating worlds. It was a game of patience and persistence. Observers added year upon year of data. Eventually, there were enough events to notice a trend. Some of the shortest events pointed to planets with masses like Jupiter, or even a few times that of Earth. The numbers seemed to tell a tale. Perhaps for every star in the galaxy, there might be many hidden planets drifting alone. With every flicker, the idea grew stronger. If these micro-lensing signals were indeed caused by rogue planets, there could be billions of them. In time, some researchers suggested that these lonely worlds might be just as numerous as the stars, or even more. It seemed that every curious signal carried a hint of immense numbers lurking in the darkness. These revelations were pivotal. Ideas that had been dismissed as speculation were now backed by real data. Rogue planets moved from the realm of myth into science. While each signal was brief, together they formed a clear image. Hidden worlds indeed drift out there. The scientific community could no longer ignore them. At last, the whispers became consensus. Through the early 21st century, evidence accumulated until the idea of rogue planets entered the mainstream. What began as an odd hypothesis was now supported by observational data. Astronomers began to acknowledge that our galaxy was home not only to orbiting planets, but to countless free wanderers. This shift in perspective reshaped how we define what a planet can be. With fresh confidence, researchers turned their attention fully toward these elusive planets. Observatories that scan the sky began tailoring their analyses to pick up the faintest hints of wandering worlds. Space telescopes peered at the galaxy in search of the ghostly infrared glimmer of a planet adrift. Every flicker and flash was now scrutinized for evidence that a lonely orb might be responsible. Scientists even began to reconsider how planets form. If so many planets wander alone, perhaps it is because star-forming regions are chaotic. Simulations showed that young planets could be expelled by gravitational tugs, making way for stable systems. Instead of questioning their existence, researchers now embraced it. Rogue planets might be as natural as their tethered cousins, born in turmoil and wandering free. In the quiet aftermath, new chapters of this story unfold. The night sky suddenly seems more alive. We have learned to look beyond the pinpricks of starlight, to consider the silent travelers among us. Although we can't see them directly, these rogue worlds have taken their place in our cosmic story. The journey to find and understand them is just beginning. For now, this chapter of exploration must pause, as another story awaits beyond the starlight. The universe holds countless mysteries still, and as we continue to listen to the quiet of the cosmos, the silent wanderers remain among our most intriguing. The journey forward is gentle and curious, for the next discovery could be just a breath away. In the quiet cradle of a newborn solar system, giant planets can begin to roam. Young stars are often surrounded by swirling disks of gas and dust, where massive planetary bodies emerge. But these giants can be cast away from home. Sudden gravitational shifts or close encounters with siblings might send them on paths that carry them far beyond the confines of their star's influence. Imagine a newborn star bright in its infancy, surrounded by a vast disk of glowing material. Within this disk, planets begin to gather form, taking shape from the swirling gas and dust. Among them, some giants emerge, massive worlds, comparable in size to Jupiter or Saturn. These young giants may start their lives in relative harmony, orbiting their star calmly, yet that peace can be deceptive. Within the newly formed planetary system, the dance of gravity can become chaotic. As multiple large worlds form, they begin to tug on each other, nudging orbits slightly closer together or farther apart. Over time, even small disturbances can grow. A gentle gravitational tug might alter a giant planet's path, setting off a series of reactions that have unpredictable consequences. One planet might find itself on a slightly tilted path, bringing it too close to a neighbor. When two giants pass near each other, their enormous gravity can slingshot one onto a different trajectory. The result can be dramatic: an orbit stretched into an extended ellipse, or even a path that spirals outward endlessly. Under the right conditions, a giant planet can be propelled beyond the edge of its solar home. Imagine two massive planets like cosmic billiard balls meeting in slow motion. Their encounter can fling one much further out, its velocity changed dramatically. Sometimes this is enough to send a planet beyond the gravitational clutch of its star. Once free of its solar tether, that wandering giant drifts alone into the darkness between the stars. This process can take millions of years, a slow evolution from stability to chaos. Initially, orbits shift imperceptibly, but each change can lead to further adjustments. If a system has several massive planets, the chance of a close encounter rises. Eventually, one encounter might be the last stable setup the system ever had. The primordial gas disk around a young star can play a role too. Gas giants may migrate inward or outward within the disk, altering the balance of the system. As the disk dissipates, planets may find themselves in unexpected orbits, no longer cushioned by gas. Without the dampening effect of the disk, interplanetary interactions can escalate unchecked. Even within a stable-looking system, danger may lurk. A gentle change in the orbit of a nascent planet may seem trivial at first, but like ripples on a pond, the effect can grow. After many orbits, the ripple can turn into a roar, sending that world flung into the void. In that moment, the cosmic balance shifts irrevocably. Once ejected, these giants become cosmic nomads. Freed from the gentle pull of a parent star, they wander through interstellar space in solitude. Some may carry with them a retinue of moons or rings, remnants of their former system. Each rogue giant is a silent traveler, a testament to the unseen forces that shaped its fate. Once cast out, a giant world drifts in the cold darkness between stars. Without its sun, the planet no longer receives the steady light that nurtured it. Its surface might freeze solid or remain dark and silent. In solitude, it travels on an endless journey, invisible on the cosmic map, unless by rare chance observed by others. Collisions in space can be unpredictable and chaotic, unlike our calm expectations. When two planetary giants meet, their encounter can resemble two slow-moving planets, merging or fracturing, rather than bouncing apart neatly. The outcome depends on mass and speed. Sometimes one planet can graze another and survive, but with changes, and other times both may be shattered. In any case, such encounters inject enormous energy into the system. The debris left behind from a collision can form belts of rock and ice. For example, a smashed planet might leave behind clouds of dust and asteroids that drift through the star system. Over time, this debris can affect surviving planets by bombarding them or even coalescing into new minor worlds. The aftermath of a collision can thus reshape the entire architecture of a system. Consider a hypothetical scenario. Two gas giants, slightly offset in their orbits, collide. The smaller one is shattered into fragments, and even the larger one loses mass, shedding an atmosphere and launching rock into space. The survivors, whether pieces or what remains of the planets, now follow new paths. Some fragments might fall back into the star, some might circle the surviving planet as rings or moons, and some might wander free. Even direct collisions that do not completely destroy a planet can severely change its trajectory. A near miss or glancing blow is enough to redirect an orbit. A planet might find itself kicked slightly outwards, stretching its path into an oval. If repeated nudges keep happening, that oval can widen until the planet roams much farther from its star. Sometimes, collisions between smaller bodies have indirect effects on giant planets. If asteroids and comets bombard a young planet, they transfer momentum. Over time, this can slightly alter the planet's motion, setting the stage for bigger interactions later on. These small impacts are like countless pebbles gradually pushing a massive boulder. The violence of a collision can propagate through space as a shockwave. Gas might ripple outward, sending pressure waves through any remaining disks of matter. Surviving planets could feel the aftermath as a shift in the distribution of gas and dust, which itself tugs on their orbits. In a cosmic sense, the collision resonates long after the immediate impact. Each collision story is different. Some lead to one planet ejected, others to a cluster of debris. The common theme is transformation. After a collision, planets find themselves in new orbits, change shapes, or gone entirely. In the cosmic ledger, collisions are recorded by what remains and what is missing. These planetary collisions often occur early in a star's life, during the chaotic phase of planet building. However, they can also happen later if a system becomes unstable. For instance, if the orbits of the surviving planets slowly drift, they may eventually cross paths and collide. No planetary system is permanent. Even mature systems can suddenly become violent after billions of years of quiet. In our own solar system's history, a period called the Late Heavy Bombardment shows us the scars of violence. It was likely triggered by a migration of Jupiter and Saturn, but it reminds us that even after planets settled, sudden chaos can break out. In other systems, that chaos might go one step further, tossing a world out of the system entirely. Each collision or series of impacts adds to the cosmic story of creation and destruction. Collisions and scattering clearly play a major role in unbinding planets. Yet another force can do the same: the complex dance of binary stars. As we've begun to explore, even without an external impact, gravitational interplay can overturn planetary order. Imagine a planet dancing under the light of two suns. In a binary star system, each star tugs at any planet present, in turn subtly warping its orbit. Over time, the combined gravitational pull can be unpredictable, especially if the two stars have a tight orbit around each other. A planet that once circled safely around one star may slowly find itself in a gravitational tug-of-war. In some binaries, a planet may orbit close to one star, barely feeling the second's influence. In others, a planet might orbit both stars in a wide circumbinary path. Either way, the presence of two gravitational sources means stability is fragile. If either star wobbles in its orbit, or if their alignment changes, planetary orbits can be severely affected. When stars in a binary approach each other, the gravitational forces spike. A planet that was once comfortably bound may be pulled away like a rubber band snapping. If the companion star grazes past at just the right distance, it can draw a planet out of orbit, flinging it into the depths of space. Even a distant second sun can, over eons, shift orbits enough to unmoor a planet. Binary systems are not rare in our galaxy. Many stars travel in pairs. This means the rulebook of planetary formation is more complicated for them. Planets that might have survived around a single star are vulnerable in a binary. The stability zones shrink, and even a long-known orbit can become unstable in the presence of a second star. Picture two stars separated by many millions of kilometers, each with a set of planets. If one star wobbles slightly in its path around the other, the planets it holds can drift in their orbits. Over time, a planet that started in a safe zone may find a slow but certain push away from its star. Eventually, without warning, it may break free and wander off. In a loose binary, where stars drift on wide orbits, the threat is slower, but no less real. A planet may circle for eons, relatively calm, until gradual perturbations accumulate. These can tip an orbit into an elongated loop that sometimes crosses paths with a distant star. The slightest extra pull at the farthest point of orbit can give the planet a final shove to freedom. In each of these scenarios, the common thread is the unseen grasp of gravity. Planets in binary systems remind us that cosmic stability is precious and rare, and while some worlds may be tossed into exile by a second sun, others might meet their doom by more delicate means. Soon, we will explore the subtleties of resonance, a gentle but relentless force that can unravel even the most orderly systems. Binary stars come in all flavors. Some circle each other very tightly, whirling around a common center like two dancers in a fast spin. Others are so far apart that each sun seems almost alone in its corner of the sky. If a planet orbits near one star, its fate depends on the distance and mass of the companion. A close approach from the companion can tug strongly, while a distant companion might only cause tiny, slow changes. Imagine a planet orbiting one star in a wide binary system. If the companion star has a long elliptical orbit, it may come around only once every few thousand years, a rare visitor in the sky. When it swings close, the gravity it exerts can shift the planet's course. Over the eons between visits, the planet may settle back into stability, but each pass carries the risk of another gravitational jolt. Now imagine a planet on a wide, circumbinary orbit, encircling both stars. In such a situation, the planet feels the gravitational tug of a single center of mass at great distance, often allowing a stable path. But if the stars themselves change their dance, for instance, if one star's orbit grows more eccentric, the combined center of mass shifts. That can introduce subtle changes in the planet's orbit, potentially leading to instability over long times. Intriguingly, some circumbinary planets have been found in our galaxy, proving these orbits are possible. These planets often orbit at great distances to remain stable, sweeping around two suns in wide circles. Their existence shows that binaries don't always send planets away. Sometimes the planets find safe havens. Yet these circumbinary homes are exceptional cases, and many other systems may not be so lucky. Even without collisions or resonance, a binary's gravitational pull alone is enough to unseat a planet. Over time, that pull can slowly pump energy into the planet's orbit. This might happen through tidal forces or by tilting the orbit. As energy is added, orbits may grow more and more stretched until a planet is nudged into a freedom-seeking trajectory. In tight binaries, the situation can be even more precarious. If a planet tries to orbit too close to two stars that are very close to each other, the gravitational field is highly complex. The planet might find stable pockets, like Lagrange points, but these are often not enough. Any small drift can send it spiraling outward, chased by the tug of the nearest star. For planets in binary systems, whether they cling to one star or both, their fate can hinge on the changing orbits of the stars themselves. If the binary stars were to gradually tighten or change eccentricity, the zones of stability for planets shrink. What was once a safe orbit could become dangerously close to the line of escape. In extreme cases, the entire system might reconfigure, casting planets outwards like debris from a churned ocean. One dramatic scenario involves a binary companion being perturbed by a passing star. As the stars dance, one might be nudged slightly by another star nearby. This shifts the gravity felt by any orbiting planet, possibly sending it onto a turbulent path. If the disturbance is strong, the planet can be flung far away during the cosmic commotion. Some star systems are more complex still. In triple star systems, the gravitational game becomes even more unpredictable. Planets in a triple system can experience the layered influence of all three suns, leading to orbital chaos. In such places, even fewer planets remain bound, as the celestial mechanics become too tangled to hold them. Binaries often form in bustling clusters of stars, surrounded by siblings. In such crowded neighborhoods, close encounters with other stars or binaries are common. These external influences can further stir the planetary pot, perturbing orbits that might otherwise remain stable. A wandering star in a cluster might dislodge a planet by tugging on its host star, adding yet another layer of complexity to the scenario. All these tales of twin stars tugging at planets underscore one theme: the delicate balance of gravity. In every case, the extra pull of a second sun changed the fate of worlds. As we step away from binaries, we look to another unseen influence: orbital resonance. This gentle but relentless force can unravel order even in a single star system. Even in a system with a single star and no collisions, unseen forces can accumulate power. Resonance is like a cosmic rhythm, where planets exert regular nudges on each other. Imagine two planets whose orbits are synchronized in a simple ratio. One might orbit twice for every orbit of the other. At each alignment, the nearer planet gives a gentle gravitational push, and over countless circuits, these tiny tugs add up. Each push is minuscule, barely altering the orbit in a single moment. But as the eons pass, these nudges repeat like a metronome. The effect can be subtle at first, but resonance can gradually warp an orbit. A planet's path can become more elongated or shifted, its orbit perturbed just enough to drift over time. Some resonances are even more intricate. In a system of many planets, multiple orbital rhythms can weave together, amplifying or negating each other. A carefully balanced dance can suddenly break down if one planet drifts slightly. Then, the once periodic nudges become chaotic variations, quickly leading the system into disorder. This process can take millions or billions of years, with the breakdown happening almost as if by surprise. One moment, the planets follow neat, clockwork orbits. The next, the alignment has changed, and orbits grow eccentric. As gravity takes its subtle toll, orbits can cross paths in new ways. Eventually, a planet might find itself nudged onto an escape trajectory. The solar system provides a cautionary tale. Though our planets are mostly in stable orbits, subtle resonances lurk. For example, Jupiter and Saturn once crossed a resonance that changed their orbits, an event that reshaped the asteroid belt and outer planets. If resonance can jolt even giant planets here, it can surely cast worlds from other systems into space. Resonance is a silent underminer of order, often working invisibly until it is too late. It reminds us that not all threats to a planet's orbit are violent or sudden. Some are subtle, changing the rhythm of motion until chaos emerges. Next, we turn to how scientists build models and predictions of how many rogue worlds might exist across the galaxy. Resonance is a hidden conductor in the orchestra of orbits. It happens when planets line up in a rhythmic pattern, their orbital periods in simple numerical ratios. This means one planet might orbit exactly twice for every 3 times another goes around, creating a constant schedule of alignments. At each meeting, their gravitational influence is repeated, and over time, like a well-timed push on a playground swing, those tiny forces build up. The effect of resonance is subtle and slow. A single alignment may tweak an orbit by a hair's breadth, imperceptible at first. But on the scale of millions of years, each tiny nudge adds to the last. Ultimately, resonance can significantly elongate an orbit or tilt it, altering a planet's path in ways a single collision might instantly do. Some resonances are more noticeable than others. In the asteroid belt, for instance, certain orbital distances are swept clean, creating gaps known as Kirkwood gaps. If an asteroid wandered there, Jupiter's repeated tugs would eventually send it elsewhere. Planets can experience similar effects. If a planet drifts into a resonant zone, it may be gradually moved out or given extra energy until it escapes the system. Picture a slow cosmic climax. 2 planets orbiting peacefully for eons until one's orbit ratio shifts a fraction. Suddenly, their alignments become synchronized, like gears clicking. With each pass, gravity tugs in the same phase, slowly amplifying their motion. Over time, the planetary orbits might begin to oscillate wildly until the next major event, perhaps a shift or even an escape into the darkness. Even if resonance doesn't lead to escape, it can still destabilize a system. A planet might develop a highly eccentric orbit, swinging in and out dramatically. This could cross paths with neighboring worlds, setting the stage for collisions or scattering. Resonance can thus act as a stealthy troublemaker, setting the stage for more explosive events later on. The solar system provides another hint of resonance at work. Long ago, Jupiter and Saturn may have crossed a 2-to-1 resonance, a cosmic double whammy. This shift is thought to have sent shockwaves through the orbits of other planets and asteroid belts. If resonance can shake up even our own backyard, it shows how powerful these subtle forces can be. Some planetary systems may harbour resonant chains, where 3 or more planets each pull at each other's orbits in rhythm. While some resonant configurations can be stable, others can be like walking a tightrope. One misstep and the balance is lost. Tidal forces, or the gradual cooling and contracting of planets, can disrupt resonance. These slow changes can move a planet out of sync, triggering a cascade of orbital shifts that might end in ejection. Resonance might even work in reverse. Sometimes, passing by orbits that resonate can capture a planet into a stable rhythm, locking it down. But if the rhythm changes pace for any reason, it can snap free. In the vast dance of planets, resonance is like the music. It can hold the dancers in step or, if it changes its tune, set them loose. Through resonance, we have seen how planets can slowly drift toward chaos, even without a bang. Now, with these forces in mind, scientists aim to tally the aftermath. In the next chapter, we will explore how researchers build statistical models to predict how many rogue worlds might be created by gravity's subtle and sudden machinations. By doing so, we can begin to count the wanderers hidden in our galaxy. Even as we explore individual paths to freedom, astronomers also seek to answer a bigger question. How many rogue worlds exist overall? They build statistical models to simulate thousands or millions of planetary systems, letting gravity play out in computer time. In these simulations, each star system can birth multiple planets that tug and collide, and sometimes throw one of their own away. By repeating the process under varied conditions, scientists estimate the frequency of ejected planets. These models incorporate known physics of planet formation and dynamics. They include factors like the number of giant planets in a system, the mass of the star, and how crowded the system becomes. Each run through the simulation might eject 0, 1, or many planets. By running enough trials, a pattern emerges. One scenario may predict that 1 in every 10 systems flings a gas giant away. Another might predict several, depending on initial conditions. Astronomers also use observations to guide these estimates. For example, surveys of our galaxy have spotted hints of free-floating planets through gravitational microlensing, a method that detects the subtle bend of light by a hidden world. Every so often, a stray planet crosses between us and a distant star, revealing its presence as a brief flash. These rare glimpses help adjust the models, suggesting that rogue worlds might be surprisingly common. Some models lean on analogies. If planetary formation yields 2 or more giants on average, the odds of instability rise. For instance, a system with 2 Jupiters is more likely to have one sent away than a system with just one large planet. Scientists might simulate 1,000 twin giant systems and find how many free-floating outcomes they get. From that, they infer how much of our galaxy's population might wander. Complex factors multiply quickly. The influence of passing stars, binary companions, and cluster environments can raise the ejection rate. Yet, the uncertainties are large. Different teams might quote different numbers, some predicting a few billion rogue planets, others even trillions in the Milky Way. The models vary, but all agree that the galaxy could be full of these silent nomads. To refine these figures, modelers must weigh each variable carefully. They adjust parameters like initial disk mass, number of young stars, or fraction of binaries. Then the simulation may be run over millions of years of virtual time to see how planetary systems evolve. From these runs, mathematicians derive a statistical picture of the galaxy's strange population of lonely worlds. Each new survey and simulation helps build this galactic census. Some models propose as many rogue planets as there are stars, while others are more conservative, predicting a smaller but still significant number. The answers are still emerging, appearing like faint signals on a dark sky. Our journey now turns to those population estimates, uncovering how scientists calculate just how many wanderers might be out there. Translating cosmic chaos into a number requires careful statistics. In one approach, researchers simulate countless star systems with different initial conditions, watching as planets are born and sometimes driven away. These virtual universes let scientists count how often ejections happen under various scenarios. By repeating this procedure over and over, a statistical map emerges of likely outcomes. One may find, for example, that systems with 3 or more giant planets often lose one, while simpler systems rarely do. These computer models must make assumptions. They choose a distribution of star masses and planet sizes, initial distances, and more. They may also incorporate binary stars or cluster effects, if relevant. Each assumption can change the outcome. For example, assuming most stars have 3 Jupiter-like planets would predict more ejections than assuming 1. Some models focus on specific galactic events. For instance, one can simulate the disruption of planets in a young star cluster, where close encounters are frequent. In such dense environments, even planets bound to stars can be stripped away by passing neighbours. By modelling clusters of different sizes and densities, researchers estimate how many rogue planets might be born in the crowded cradles of stars. Astronomers also integrate observational data to constrain these models. They take cues from how many exoplanets are found per star on average. If, say, surveys indicate that multi-planet systems are common, that informs the initial conditions. They also consider the metallicity of stars, the typical lifespans of disks, and other properties gleaned from telescopes. Even then, predictions come with uncertainty. Rogue planet counts can vary by orders of magnitude between models. One model might suggest the Milky Way has only a few billion. Another might suggest tens of billions. Researchers often compare their results with actual lensing survey outcomes to see which numbers match reality. But since observations are still sparse, theory continues to explore a wide range of possibilities. Certain surveys provide clues. Gravitational microlensing experiments have reported hints of Jupiter-sized objects not attached to stars. If confirmed, those detections would imply a minimum count of free-floating giants. However, some of these could be more massive, failed stars, called brown dwarfs, and distinguishing them is tricky. Analysts must carefully model the likelihood that each microlensing signal comes from a rogue planet rather than another source. Beyond microlensing, there are upcoming missions that could change the game. The future may bring space telescopes designed to hunt for such faint, cold objects through infrared surveys. Each new generation of technology refines the statistics, reducing uncertainty. For now, scientists work with what they have, steadily building a more precise estimate of how many wanderers populate the galaxy. In short, building these statistics is like assembling a cosmic census. It blends theory and observation, mixing our best models of planet formation with glimpses of reality. The result is still a bit fuzzy, but gradually coming into focus. In the next chapter, we will present these numbers and their implications, painting a picture of the galaxy as a galaxy of wanderers. Even as we refine our understanding, the emerging picture is astonishing. Models vary, but some predict roughly 1 to 10 free-floating giant planets for every 100 stars in the galaxy. Others are more daring, suggesting a ratio of 1 rogue per star, especially if planetary systems often spawn multiple giants. These guesses might seem wild, but they come from carefully tallying outcomes across many simulated universes. The true number likely falls somewhere in between. To put this in perspective, the Milky Way has about 100 billion stars. Even a conservative estimate of 1 rogue per 100 stars means a billion wanderers. If the higher estimates hold, the galaxy might teem with tens of billions of unattached planets. This would transform our picture of the night sky's darkness into a rich ocean of hidden islands. Such vast numbers have implications beyond counting. Rogue worlds might carry chemicals or materials from their birth systems into the interstellar medium. They could seed new regions of space with elements that might never otherwise travel so far. The idea is speculative, but it suggests that wanderers are not just passive drifters. They might play a role in the galaxy's ecosystem. By building these statistics, astronomers aim to calibrate our understanding of planet formation on a cosmic scale. Each number in the models encapsulates assumptions about how systems work. As more data comes in, researchers adjust the parameters, narrowing the possible range. The result is an evolving consensus, painting a picture of our galaxy with many secret planets traveling between the stars. As we tally up these wanderers, one thing becomes clear. The galaxy may be far more populated than it looks. Each dark patch in the sky could hide a drifting world. If even a fraction of predicted rogues exist, the total number may reach into the billions or more. This abundance challenges our ideas about where planets belong and what their numbers really are. If the estimates are correct, our Milky Way could be teeming with lonely worlds. Some scientists propose that there may be as many rogue planets as there are stars. Even if this is an upper bound, we are still talking about tens of billions of worlds. Picture all those planets, each a small island of matter moving through the cosmic ocean, mostly unseen by telescopes. This has practical implications for astronomers. For one, it changes how we plan searches for planets. If many planets have no star, we need to search the dark directly for their heat or gravitational effects. Upcoming missions are being designed to look for these elusive worlds by their faint glow in infrared or by the bending of starlight they cause. Each detection will help piece together the puzzle, gradually illuminating the true extent of this hidden population. Some scientists have even speculated about the role of rogue planets in the broader cosmos. Perhaps they contributed to spreading water or organics. A wandering planet could, hypothetically, bring ices from one system to another. While these ideas are speculative, they invite us to think of planets not just as bound to their stars, but as possible messengers in the galaxy. The existence of countless rogue worlds also has philosophical implications. It reminds us how much of the universe's story remains hidden. A planet adrift has no sunrise or sunset, yet it is a world nonetheless, with its own potential history. Imagining these dark wanderers expands our perspective on what home might mean for a planet. It could be a journey without a fixed address. Their presence in vast numbers could even subtly influence galactic dynamics. Though individually small, collectively their mass might contribute to the gravitational potential of the Milky Way. Some researchers wonder if rogue planets make a slight contribution to what we attribute to dark matter. It seems unlikely they can solve the dark matter mystery, but they add a twist to the tale of galactic mass distribution. On a more local scale, every now and then a rogue planet could wander near a solar system. If our Sun had such an encounter in the past, it might have stirred the Oort cloud of comets, sending long-period comets inward. Some have proposed that periodic comet showers could be caused by such a passing interstellar planet. While evidence is speculative, it illustrates that these wanderers might occasionally make their presence felt. Our own solar system might have had its own rogue in the past. There is a hypothesis that Earth or Neptune might have once been part of a pair, with one being thrown out long ago. If a super-Earth once orbited our Sun in a distant orbit and was ejected, it could explain some odd features of our system. Such ideas remind us that our planetary neighbourhood may have been shaped by events that created our own wanderers. Considering the sheer number of possible wanderers, one can't help but wonder, could any of them harbour something? A rogue planet with a thick atmosphere could retain internal heat, potentially allowing liquid oceans beneath an ice shell. Even if the surface is frozen, it might have geothermal warmth inside. Though speculative, these ideas suggest we should not dismiss rogue planets as entirely barren. They might be dark, but not necessarily lifeless worlds. The story of rogue worlds remains open-ended. Astronomers continue to search, refine models, and imagine the possibilities. Each new discovery could add to this unfolding narrative, making us rethink what it means to be a planet. Our odyssey is far from over, and as long as the stars shine, we will keep asking what other secrets the darkness holds. On a free-floating gas giant, Storms would still rage unseen. Jupiter's great red spot, a vast hurricane twice the size of Earth, could continue its long fight against decay, fueled by the heat within. The colourful bands of the planet, swirls of orange, brown and white, would not vanish, but without sunlight, their pigments would dull and merge. Lightning might still flash in these clouds, briefly illuminating the darkness above. In eternal night, such flashes would be the only moving lights, sudden flares of energy in an otherwise still sky. Beneath the clouds, winds would still howl at hundreds of kilometers per hour, driven by the slow release of internal heat rather than sunshine. The planet's weather would proceed quietly but powerfully, a silent storm system that we can only imagine from afar. Even their weather would carry echoes of the old order. Jupiter's winds, driven more by internal heat than by the sun, would still blow with great strength. The great red spot, an enormous anticyclonic storm, would continue to churn, though it might gradually shrink and fade without fresh heat injection. Other banded storms and jet streams would persist, sculpted by the planet's rapid rotation. Without sunlight, colours would fade. Bands of orange and white might blend into grey. Clouds would rain out what little they still contain, making the atmosphere more transparent and still. Storms would produce thunder and lightning as usual, but the sound would echo into the void with no warming sun to gild the skies. On a free-floating gas giant, storms would still rage unseen. Jupiter's great red spot, a vast hurricane twice the size of Earth, could continue its long fight against decay, powered by the heat within. The colourful bands of the planet, swirls of orange and white, would not vanish, but without sunlight their pigments would dull and merge. Lightning might still flash in these clouds, briefly illuminating the darkness above. In eternal night, those lightning flashes would become lonely beacons of activity. While the sky stayed black, each thunderous burst of electricity would momentarily light up the cloud tops. Beyond that, the planet's weather would proceed quietly. Pressure systems would shift slowly, and winds would howl beneath the ice-cold air. Even without solar warmth, the giant's atmosphere would remain a place of fluid motion and occasional fury. Gas giants are mostly hydrogen and helium, the same elements that light up stars. Their enormous pressure compresses hydrogen into exotic forms. Deep inside, hydrogen turns metallic and conducts electricity. This powers their immense magnetic fields, even without a sun. In interstellar darkness, these layers are unchanged, but any lighter gases in the outer envelope simply grow colder and darker. Under frigid skies, even the familiar clouds of ammonia or methane in Jupiter's atmosphere sink and condense into deeper layers. Only heavier gases remain aloft, giving the atmosphere a more uniform and muted appearance. A drifting Jupiter would be like a colossal planet-sized battery, maintaining its fields by internal energy. Its belts of charged particles would still encircle it, but shaped differently by the silent space. Without solar wind, the magnetosphere would shrink to its planetary cocoon, yet Io's volcanic particles could keep polar lights dancing. Even without a star, the giant's magnetic storms might continue, creating auroras fueled by its own rotation and moons instead of the sun. Deep down inside, exotic processes would continue. Hydrogen, under immense pressure, becomes metallic, potentially giving way to diamond rain deeper down, as predicted for ice giants. Helium, being immiscible in metallic hydrogen, could condense and rain toward the core, releasing more heat. Clouds of water or ammonia would sink to new depths as the atmosphere cools, perhaps forming ice crystals at unexpected levels. In this frozen state, parts of the interior might exist as liquid metallic hydrogen under pressure. These internal processes would keep the giant glowing faintly in infrared long after it left its parent star. Though free-floating, the giant will not cool quickly. Such large bodies have enormous heat capacity. Even without a star, it would take many billions of years to lose most of their heat. In that time, the core slowly cools and the planet contracts slightly. Only after eons will the entire envelope become so cold that molecular motion nearly stops. By comparison, the universe itself is on the same scale of age. These planets will remain active far longer than the lives of most stars. Alone in the galaxy, a rogue world will journey through empty space. It may traverse spiral arms and star clusters on its orbit around the galactic center. Occasionally, it might pass near another star, brushing through cosmic neighborhoods that once nurtured life. During such a flyby, the planet might briefly warm on one side, but it would still be doomed to wander. Barring capture, it will continue indefinitely on a lonely path, unseen by casual stargazers. Imagine gazing up from the giant's cloud tops. There would be no sunlit sky, only eternal night. The band of the Milky Way might stretch faintly overhead, but without a sun, even the galaxy's glow would seem dim. Stars would appear like scattered jewels on black velvet. But this would never end. The only brightening might come from unexpected sources, a distant supernova, or even the planet's own faint auroras at the poles. Otherwise, it would be a universe without dawn or dusk, a perpetual midnight dominated by distant starlight. Not all wanderers are giants. Imagine a distant planet, the size of Earth, drifting alone. Unlike a giant, an Earth-sized world has no thick blanket of hydrogen to trap heat. It is composed of rock and metals like our own. In the cold of space, its surface becomes an icebox. Any water or gases freeze solid. Oceans and lakes turn to ice. And the sky, if it had one, turns from blue to black as gases collapse. Even smaller, a lonely planet might be more like a snow-covered rock. It could be a world of rock and ice, with crusts of frozen water, ammonia, and methane. Such a planet would feel more like a comet than an Earth. Its day side would be as cold as the depths of space, just a few tens of degrees above absolute zero. Without a star, the only light would come from distant galaxies, rendering the surface pitch black. Any lakes or seas long ago hardened into solid ice under the frigid skies. Yet if the planet contains radioactive elements, that buried heat could slowly shift the ice or melt it from beneath. Over eons, heat from the core might allow a secret ocean to persist under kilometers of frozen crust. In this icy silence, seasons and weather, as we know them, disappear. With no sunshine, there are no days or nights, no seasons. The air, if any remains, would be nearly motionless. A frozen world might have only a wispy atmosphere, nitrogen, methane, or carbon monoxide. And even this could collapse into frost under the extreme cold. If the planet had a magnetic field, it might interact faintly with cosmic rays, sparking rare aurora glows. But mostly, such an icy wanderer would be eerily still and silent, an eternal winter world traveling alone. Even medium-sized rockers suffer a similar fate. An Earth-like world, if banished from its star system, would turn into a frozen wasteland. Its forests, deserts, and oceans would vanish under a sheet of ice. The sky would lose any ozone, and the air would rain down carbon dioxide and nitrogen as ices. Mountains once warmed by day would crack and fracture under unending cold. Volcanic vents might keep small regions slightly warmer, creating thin pockets of warmth amid the frozen plains. But for the most part, The planet's surface would settle into pitch-black stillness, illuminated only by the occasional flash of cosmic rays or distant starlight. Some mid-sized rogues could harbour hidden oceans. A planet a bit larger than Mars may have enough radioactive heat to maintain a subsurface liquid layer beneath kilometres of ice. It would be covered by a thick ice shell, but deep down there might be a salty ocean warmed by the core. These worlds might be ice-covered twins of Europa or Enceladus, with water kept liquid out of sight, though their surfaces are frozen solid. Deep beneath the ice, liquid water could persist in a hidden sea. Some rogue worlds might still rumble beneath the surface. If heat and pressure are right, icy volcanism could occur. Enceladus-like geysers might erupt, spewing water or ammonia into the dark sky. These plumes would quickly freeze in the cold, but they hint at an active interior. Even rock-based worlds could have ice volcanoes, where slushy mixtures flow outward. Such mysterious activity would contrast sharply with the frozen exterior, a hidden sign of a dynamic interior. Not every wanderer is planet-sized. Even small worlds can drift alone. Imagine a body only a few hundred kilometers across, bigger than a city, but smaller than a moon. If it were ejected, it would freeze solid. Its ice and rock would cool to just a few tens of degrees above absolute zero. Such an object would resemble a giant icy boulder, dead and inert. Only minute internal decay might warm its center slightly, but the surface would be a dull, dark object in the void. Even large icy worlds lose their sky. Consider Titan, Saturn's moon with its thick orange haze. Its atmosphere is held aloft by only a trickle of sunlight. Without that energy, Titan's nitrogen and methane would rain out and freeze solid. A Titan cast into interstellar space would quickly become just another frozen moon, its skies cleared and its lakes turned to solid hydrocarbons. In a universe without a sun, most atmospheres simply collapse into the ground. In truth, these icy wanderers could be extremely common. Astronomers suspect that for every star in the galaxy, there may be at least one or more such planets. If even a fraction of those are small, we may have billions of cold worlds filling the space between stars. They are the unlit majority of planets, hidden in the darkness. Yet each one carries the legacy of a lost solar system, drifting forever on a lonely path through the galaxy. As wanderers grow more massive, they start to challenge our categories. What do you call an object at the boundary of planet and star? Astronomers often draw the line at the deuterium burning limit, about 13 times Jupiter's mass. Above that threshold, an object can fuse deuterium briefly, so some call it a brown dwarf rather than a planet. But others insist that how it formed, in a disk or in isolation, is the true distinction. The debate goes on. Defining them precisely has proved tricky. The International Astronomical Union hasn't set a clear rule for these drifters. By one definition, a planet must orbit a star, so none of these truly qualify by that strict rule. Yet the term free-floating planet is widely used because they behave so much like planets in mass and appearance. In practice, many astronomers use mass-based definitions, treating anything below the deuterium fusion threshold as planetary mass, regardless of orbit. Ultimately, these choices of words are just attempts to impose order on nature's rich variety. The truth is, the border between planet and star is blurry. Our language struggles to describe these objects. Some astronomers speak of sub-brown dwarfs or planetary mass objects, terms that capture the uncertainty. Brown dwarfs are often discovered in star-forming regions, glowing faintly in infrared light. They have enough mass to burn deuterium early on, but not enough to ignite full hydrogen fusion like the Sun. In contrast, A true rogue planet would have formed around a star and lost it somehow, but both can end up with similar masses and atmospheres. We simply do not know in many cases whether an object wandered away from a star or was born in isolation like a tiny star. In fact, some of our closest cosmic neighbours belong to this mysterious class. Telescopes have uncovered brown dwarfs just a few light years away, each only a fraction of the sun's mass. They glow feebly, like embers barely glowing in a dying fire. One of the coldest such neighbours is so chilly that it could almost be called a rogue planet by another name. At those close distances, even objects of planetary mass become visible in the infrared, yet remain invisible in starlight. They sit in the darkness of space, challenging our definitions of planets and stars. Interestingly, some of the coldest brown dwarfs discovered are only a few hundred degrees above absolute zero, about as warm as a hot spring or a summer afternoon on Earth. This means they are warmer than we might expect, thanks to their youth or leftover heat of formation. Imagine a world without a sun, yet as warm as a spring day at its core. By studying their light in the infrared, astronomers see hints of water vapor and clouds in their skies, features we normally associate with planets. These free-floating objects thus look more like planetary siblings than true stars, even though they wander where a planet might. Clues to their origin come from their surroundings. In young star clusters, astronomers see objects of planetary mass roaming freely. Some of these have dusty disks, like young stars, suggesting they formed in isolation. Others appear as stray planets that likely got flung out. When a brown dwarf forms like a star, it can collect a disk that might form its own little system of satellites. If that system were ejected, the brown dwarf and any moons would drift through space together. Astronomers have even classified these free-floating objects with star-like labels. Some are called brown dwarfs of spectral type L, T, and Y, based on their colour and temperature. The Y dwarfs are the coolest, sometimes just a few hundred degrees above absolute zero. In fact, we have found Y dwarfs radiating only a little heat, as warm as a campfire on Earth. Others are warmer, overlapping the coolest giant planets in temperature. Each new spectral class blurs the planet-star divide further. Between the heaviest planets and the lightest stars lies a grey zone. A brown dwarf, about 12 to 15 times Jupiter's mass, can briefly fuse deuterium early on, creating an internal glow. In contrast, a 10 Jupiter mass planet never does this, but after the first few million years, they all simply cool down and look alike. Without a star to illuminate them, both brown dwarfs and giant planets fade to black, except in the infrared. In practice, astronomers often rely on indirect clues or formation history to distinguish them. Interestingly, some surveys suggest these wandering masses might even outnumber stars. One microlensing study inferred that there could be as many as 2 gas giant wanderers for every star in our galaxy. If true, these unbound worlds would be the galaxy's majority, hidden in darkness. That doesn't settle their identity. Most of these could be either tiny brown dwarfs or massive planets, but it emphasizes how many are lurking unseen. Whether they came from dislodged star systems or formed like small stars, their existence adds a new dimension to the richness of our Milky Way. Despite the cold void outside, inner warmth may endure. One hidden source is radioactive decay. Elements like uranium and thorium inside a planet's core slowly generate heat for billions of years. On Earth, this decay still powers a large fraction of our geothermal energy. A rogue planet carries the same ingredients. Under kilometers of rock and ice, its radioactive furnaces send heat outward, preventing the entire planet from freezing solid. Over eons, this internal fire can keep oceans liquid and drives geology long after stellar light is gone. Consider an Earth-like rogue. With no sun, its surface would fall to a chilly few tens of kelvins. But its deep interior would stay surprisingly warm. Earth's core, for instance, still churns at over 5,000 kelvins today. The decay of even a few radioactive atoms per minute beneath our feet adds up to about 40 terawatts of heat globally. In interstellar space, that same heat could melt rock and sustain volcanic activity underground. Such a world might look dead on the surface, but beneath the ice, it could remain alive with geologic force for a very long time. Tidal forces can also be important heat sources. If the rogue planet retained a large moon or companion, their mutual gravity could flex each body. This is how Jupiter keeps Io molten and Saturn powers Enceladus's geysers. In interstellar space, even a distant moon could twist the planet's interior with each orbit. The friction from this invisible dance would warm the rock and ice within, sometimes intensely. In theory, two planets orbiting each other as they drift could knead each other's cores, unlocking heat just as in a cosmic duet. These hidden heat engines, while speculative, show that even in endless night, a world can stay warm from within. Gravity itself can keep a rogue planet warm, albeit weakly. Gas giants radiate heat as they slowly contract over time, a process called Kelvin-Helmholtz cooling. A solitary Jupiter is still shrinking by a few millimeters each year, releasing gravitational energy. This unseen process generates additional heat. Even rocky worlds compress slightly under their own gravity, though that effect is much smaller. Over cosmic time, these contractions add only a little heat, but in the early eons, they can bolster the initial internal fire. Together, these hidden heat sources mean that a rogue planet can stay warm inside for eons. It is as if the world carries a small, buried hearth. Though its surface may be frozen in darkness, the interior glows with warmth and activity. Over time it will cool and the fires will die, but that process is measured in billions of years. In the meantime, the planet is anything but dead. Beneath the ice, or deep in the core, it could remain surprisingly alive with geologic force. Astronomers can even detect this hidden warmth from afar. A young or massive rogue will shine more brightly in the infrared due to its heat. By measuring that glow, scientists estimate how much internal heat remains, and even guess the planet's age. In effect, these planets carry their own headlight. As the heat leaks away, the light fades, so a dim rogue is likely very old. Each detected faint glow is a clue to the secret furnace burning within. We can see evidence of this heating even now. Jupiter emits roughly 70 terawatts of power, about 1.5 times the energy it receives from sunlight. That extra energy is from its interior heat. If Jupiter were isolated in space, it would still radiate those 70 terawatts into the void. In fact, its infrared brightness tells astronomers that it will take trillions of years for Jupiter's core to cool fully. In effect, Jupiter is already a kind of dim brown dwarf in disguise, slowly fading into the cold. The size of the planet matters a great deal. A small Earth-sized rogue has far less heat to give and will cool faster, while a Jupiter-sized giant carries a tremendous energy budget. As a rule, the bigger the planet, the longer it glows. A Mars-like world might freeze almost solid in a few 100 million years, whereas a gas giant can stay hot for hundreds of billions or even trillions of years. Thus, massive wanderers remain warm echoes of their youth long after smaller planets go dark. Without a star's breath, atmospheres take on new fates. Large planets generally have strong gravity, so they can initially hold thick envelopes. a free-floating gas giant, would keep its hydrogen and helium layers, perhaps even contract slowly under self-gravity. But smaller worlds fare worse. A rocky rogue the size of Earth or Mars has relatively weak gravity. It would likely lose any hydrogen long before ejection. In the icy dark, lightweight gases move too fast to stay. Hydrogen and helium escape into the void, leaving behind only heavier vapors, if anything. Even heavier gases soon collapse. On a rogue Earth, at a few tens of kelvins, familiar volatiles would solidify. Carbon dioxide and nitrogen would become solid ice on the ground. Water would remain frozen as its usual ice. Very little would stay in the air. Only perhaps a bit of methane or other trace gases might linger at most. Essentially, a small rogue planet's atmosphere would collapse into the surface, leaving almost no gas to speak of. One counterintuitive possibility is a thick hydrogen blanket. Hydrogen, though light, can produce a potent greenhouse if it's dense enough. A massive envelope of hydrogen and helium around a rogue world acts like an insulating thermal blanket. Under hundreds of bars of pressure, such an atmosphere would trap internal heat and raise the surface temperature. Theoretical models show that an Earth mass rogue with a huge hydrogen envelope could maintain liquid oceans beneath the clouds. Whether a planet can retain such a thick layer of hydrogen depends on its mass and formation history. But if it does, the world could be surprisingly warm inside the darkness. Without sunlight, cosmic factors become more important. There is no solar wind to strip away gas, which helps an atmosphere survive. But cosmic rays and interstellar particles can slowly erode an upper atmosphere over eons. Rogue planets traveling through the galaxy might occasionally pass through a molecular cloud and even pick up some gas, though this would be very thin. Overall, a rogue sky is not completely permanent, but compared to a sunlit planet, it changes only very slowly. In summary, a rogue planet's atmosphere is generally fragile. Only the largest, most massive worlds are likely to keep substantial gas. Smaller wanderers will see their skies thin into nothing or collapse into ice. If we ever observe a free-floating world with a rich atmosphere, it will probably be a behemoth, likely a gas giant or mini Neptune, to have done so. Otherwise, most interstellar planets are essentially airless, with their true nature hidden beneath frozen surfaces. Astronomers have developed clever ways to track these dark wanderers. In infrared light, even a lonely planet emits heat. Telescopes like the Wide Field Infrared Survey Explorer, WISE, and the Spitzer Space Telescope have picked out faint infrared points in the sky. These surveys flag candidates, faint objects only a few hundred kelvins in temperature, often classified as Y dwarfs. Follow-up observations try to distinguish true, free-floating planets from ordinary brown dwarfs. Astronomers look for motion. A nearby rogue planet will drift noticeably against the background of distant stars over months or years. They also study the object's spectrum for clues of its atmosphere. If it shows features like methane and water vapor, that strengthens the case that it is a planet-like world. In this way, each dim glow is scrutinized for the telltale signature of a wanderer. Ground-based surveys like OGLE, MOA, and KMT-NET continuously monitor dense star fields to catch gravitational microlensing. Telescopes across the world coordinate to watch the same patch of sky day and night. When a rogue planet passes precisely in front of a distant star, its gravity can briefly magnify the star's light. These lensing events are short, often only hours or days, and if no star is seen at the lens, it hints at a free-floating planet. Dozens of such candidate events have already been found. Future missions will greatly expand this method. For example, NASA's Roman Space Telescope will spend months staring at the galactic center, expected to detect hundreds of microlensing events caused by isolated planets. Each observed flash of light without a host star adds to our map of the hidden population. Remarkably, we can even listen for these wanderers. Instead of light, they may announce themselves through radio waves. Astronomers have detected exactly that, an isolated, planet-sized object pulsing in the radio spectrum. The signal had a periodic beat, like a distant lighthouse horn, emitted by strong auroras in the object's magnetosphere. This rogue world, about 12 times Jupiter's mass, became the first of its kind heard in radio. Its magnetic field must be enormous, channeling charged particles to create radio emission. This landmark discovery suggests that radio telescopes can tune into the galaxy's nomads. Telescopes like LOFAR and the upcoming Square Kilometre Array will scan the skies for these cosmic beacons. Even without a star to spark them, strong fields and storms on these giants can sing in radio frequencies. In the coming years, astronomers hope to catch many more of these silent planets by their whispers in the radio. Astronomers train their instruments night after night, following the faint drift, or the slight glow, or the distant hum. Though invisible to our eyes, these lonely planets leave subtle fingerprints that we are just learning to read. Their silence hides secrets, and each discovery reminds us of the vast unknown. The cosmic sea remains mysterious, and our exploration has only just begun. Listening and looking ever deeper into the void for the next whisper of a world adrift. For eons, the planets we know have faithfully circled their suns under warm starlight. But now, imagine something utterly different. Picture an Earth-mass world, untethered to any star, drifting alone through the infinite night. Its sky would never brighten with dawn or twilight. Instead, the heavens would be an endless ink-black canvas, studded only by distant stars and the faint band of the Milky Way. To an observer on that frozen world, the familiar sun would never rise, and no sunrise colours would ever appear. Constellations would wheel silently overhead, tracing the slow rotation of the planet, but there would be no change in light or dark, only constant, absolute night. At first glance it would seem utterly desolate, bare ground and ice, silence in all directions. Yet appearances can be deceiving. Beneath that frozen shell could lie warm secrets. Imagine standing on the surface of this forlorn planet. The cold would bite through any clothing. Your breath would freeze on the instant of exhalation, forming delicate ice crystals in the air. The ground beneath you would be rock or dirt coated in frost. Footprints would crackle under your boots as you walk. The landscape would be motionless. Still snowfields, jagged mountain silhouettes under black sky, extinct volcanoes frozen in time. There would be no wind or weather systems to stir snowstorms or clouds. The air would be as still as space itself. In the sky above, stars and distant galaxies would shine brightly, perhaps shimmering with rare meteors streaking by. But no moonlight or aurora would interrupt the void. All warmth would come from below your feet, not above, and all light from without. Despite the grim cold, we shall see that this world might not be entirely barren of life. How can such a rogue Earth come to be? In the chaos of a newborn solar system, planets are like cosmic pinballs. Gravity tugs them into strange dances, and near misses can send one careening out into the void. Imagine a young Earth bumping into a sibling world or being swept up by a roaming giant planet. A passing star might yank it clear of its sun, or the violent explosion of a nearby star might blast it away. In such cosmic billiards, a planet once in the Goldilocks zone could find itself flung into darkness. In some dramatic account of cosmic formation, an Earth-like world is born only to be hurled into interstellar space before it has time to warm under any sun. As strange as it sounds, rogue planets may not be rare oddities, but surprisingly numerous. Recent astronomical surveys using gravitational microlensing indicate our galaxy could host dozens of starless planets for each star. If that is correct, the Milky Way might contain hundreds of billions to perhaps a trillion rogue planets. In our own stellar neighborhood, the nearest one might be only a few light-years away, silently coasting through space. Some researchers even suggest the Sun itself could have a hidden companion drifting in the outer solar system, unnoticed. In effect, our picture of the local cosmos changes. Instead of empty darkness between stars, there could be many invisible worlds roaming the galaxy. These wanderers come in many forms. Some are gas giants, Jupiter or Neptune-sized planets cast out alone, frozen to near 0 Kelvin. Others are smaller, rocky worlds, rogue Earths of rock and metal. It is the latter that intrigue us most when we wonder about hidden habitability. A rocky rogue would still have an iron core and silicate mantle, perhaps even mountain chains and dry riverbeds once carved in distant eras. In these icebound scenes, volcanoes would lie dormant and rivers long frozen. Yet deep inside, that familiar geology might persist. Of course, a lone planet without a sun would eventually freeze over. Without sunlight, its atmosphere would condense. Nitrogen, oxygen, and other gases would collapse into frost on the ground. But deep below the surface, the planet's interior heat might continue to flow. What happens when an Earth-like planet loses its sun? The transformation would be swift and severe. Surface water would begin to solidify almost immediately, forming thick ice sheets that grow kilometre by kilometre. In the same moment, the atmosphere itself would freeze. Nitrogen and oxygen liquefy and solidify at tens of kelvins, leaving almost no air. Global temperatures would plummet from a comfortable 15 degrees Celsius to just a few dozen kelvins above absolute zero. The planet would become like a giant comet or distant dwarf planet, its oceans turned to an endless ice shell. In this frigid state, the world would bear little resemblance to a hospitable Earth. Yet one source of warmth remains: the planet's own internal heat. The core, still hot from formation and ongoing radioactive decay, would continue to send energy outward. In fact, for a time that might be all this planet has for warmth. There is one exceptional scenario worth noting. If a rocky world managed to retain a deep hydrogen-helium envelope from its youth, that gas cocoon could trap heat efficiently. Hydrogen at high pressure is a potent insulator. Some models show that a thick hydrogen blanket might keep the surface far warmer than the freezing space outside. In such a case, the effective temperature of the planet could be only around 30 Kelvin, but the actual surface might stay warm enough for liquid water, perhaps near the temperature of Earth's deep oceans. This is a rare possibility, because Earth-sized planets usually lose such thick atmospheres early. But it reminds us that any way to hold heat in can help. Even without a special atmosphere, all is not lost. Over eons the ice would thicken, but also insulate. Kilometers of frozen crust would act like an insulating blanket over the interior. Deep below, the decay of uranium, thorium, and potassium in the rocky mantle would continue releasing heat just as it does on Earth. In time, one can imagine a cold, static exterior cloaking a hidden ocean. Insulated beneath the ice, liquid water could persist. In fact, If the planet had been ejected when still warm, its interior might remain hot enough to keep an ocean liquid for billions of years. The ice outside, ironically, protects that warmth. In effect, a rogue Earth might become a kind of cosmic snow globe, frozen on the outside but steaming within. If such a hidden ocean exists, what might it be like? Consider the icy moons of our own solar system. Jupiter's moon, Europa, is encased in about 20 kilometers of water ice, yet beneath it lies a vast, salty ocean, kept liquid by tidal flexing and internal heat. Saturn's moon, Enceladus, despite being small and far from the sun, has spectacular geysers venting from a subsurface sea. Other moons, Ganymede, Titan, even Pluto, likely hide remnant oceans under ice. These examples demonstrate that ice-covered oceans can thrive without direct sunlight. A rogue planet, though different in scale, could operate on the same principle. Its ice shell, tens of kilometers thick, would be the insulating roof of a hidden sea. Pressure from this ice would be immense, hundreds of times that at Earth's surface. That pressure helps keep water liquid at low temperatures. In fact, under extreme pressure, water can remain liquid down to well below 0 degrees Celsius. High-pressure ice phases might form layers in the shell above, but at the bottom, heat flow would keep water liquid. The ocean itself might be very cold and salty, akin to Earth's deep southern ocean beneath Antarctica's ice, with brines lowering the freezing point. Dissolved minerals and gases from the rocky floor would saturate the water, providing nutrients. With no wind or weather, ocean currents would be driven solely by geothermal upwelling, slow plumes of warm water rising from seafloor vents. Remarkably, such hidden seas would be quite stable. Without seasonal changes or storms, they would simmer in darkness for eons. The interface between ice and water might slowly creep over geological time, but large liquid regions could persist. Hydrothermal vents on the ocean floor would act as underwater geysers, spewing heat and minerals into the dark water. These vents would create warm oases in the cold, much like they do in Earth's oceans. One can imagine entire ecosystems of deep ocean vents, sustained by nothing but the planet's internal fire. Indeed, the thought of an ocean in eternal night forces us to rethink habitability. Traditionally, we spoke of a planet's habitable zone as its distance from a star. But our hidden ocean shows that the habitable zone can be hidden within a planet itself. If liquid water persists and an energy source exists, life might find a foothold even far from any star. In our next chapter, we'll explore what such life might be like. Without the sun's light, these dark depths would rely entirely on chemical energy. On Earth, we see life thriving this way. In the deep ocean, bacteria feed on hydrogen sulfide or methane emerging from vents, converting these chemicals into biomass. Tube worms, clams, and shrimp form ecosystems around these bacterial communities, completely independent of sunlight. On land and under ice, microbes metabolize iron, sulfur, or ammonia from rock and ice. A rogue planet's subsurface ocean would likely contain similar ingredients: hydrogen from rock-water reactions, sulfur or iron from the mantle, perhaps methane clathrates in the sediment. If any life could tap these molecules, chemosynthesis could fuel an underground biosphere. Some have even imagined more exotic energy sources. If a rogue drifted near a galaxy's active center, intense radiation might allow a feeble kind of photosynthesis, though that is far-fetched for most. Cosmic rays striking the atmosphere could produce reactive compounds. Still, for all practical purposes, any hypothetical life in a rogue ocean would live off the heat and chemistry from below. In a way, the planet's core would become the sun of that world, the source of energy that drives every food web. What would the inhabitants of this eternal night be like? They would almost certainly be very different from familiar surface creatures. There would be no bright colours or eyes built for daylight. Instead, life would huddle around the vents and warm spots on the seafloor. We might expect mostly simple, slow-growing organisms. Creatures might resemble the worms, clams, and crustaceans around Earth's vents. Perhaps tube worm-like beings with blood-like pigments to shuttle energy, or blind, eel-like swimmers that navigate by vibration or chemistry. On Earth, cave and deep-sea animals have no eyes and no pigment. Similarly, a rogue world's creatures would likely be pale or transparent. They might have long antennae or tentacles to sense chemicals and touch in the dark. Without photosynthesis, there would be no forests or swarms of plankton. Instead, colonies of microbes and small animals would form the base of the ecosystem. Growth and movement would be very slow. There's only so much energy to go around in such a cold place. We can only speculate, but these creatures would probably lead quiet lives. Food chains would be simple. Bacteria and archaea at the bottom, small grazers eating them, and perhaps a few predators at the top. Population densities would be low because energy is precious. On Earth, some deep-sea microbes divide only once every few years. On a rogue world, reproduction might take decades. Even so, their existence would be a testament to life's adaptability. In this way, a rogue planet's hidden ocean could indeed become a cradle of shadowed life. The possibility of life in eternal darkness forces us to rethink our definition of habitable. For a long time, we equated habitability with a planet receiving sunlight at just the right distance, the so-called Goldilocks, or habitable zone. But life on a rogue world has no sun. This means the traditional habitable zone concept is too narrow. Instead, we see that any world with liquid water and an energy source, whether from a star, its core, or chemistry, could potentially be habitable. In other words, habitability should be defined by conditions, not by orbit. Europa, Titan, and Mars are considered potentially habitable, even though none is squarely in the Sun's temperate band. By that logic, a rogue planet with a subsurface ocean and heat could qualify as habitable. In practical terms, this broad view changes how we search for life. Our probes and telescopes should look for liquid water and energy flows anywhere they may occur, not only around stars. Missions to subsurface oceans on moons already reflect this thinking. The key question becomes, does an environment have liquid water and a steady energy source? If yes, it may be a home for life. It's a humble reminder. Life on Earth itself survives in hot springs, deep mines, and icy caves. Once we discovered those, we accepted them as habitats. Likewise, we must be open to worlds unlike our own Earth-Sun relationship. We may even arrive at the philosophical stance that habitable simply means able to support life, period, wherever that may happen to be. Throughout history, our concept of habitability has expanded. For centuries, we sought only Earth-like planets in Earth-like orbits. Today, we realize that any wet, warm spot could work. A world that once seemed utterly dead might hold oceans full of life below. This is a profound shift. It means the Milky Way could host far more habitable environments than we ever imagined. Importantly, even if a rogue planet has no life now, its conditions could in principle allow life to take hold. As we broaden our view of habitable worlds, our journey does not end. We have pictured rogue planets adrift and possibly alive in the dark. Now we ask, what is the next twist in their story? Could these wanderers find stars to orbit once more? This leads us to the final chapter of our exploration. We have imagined rogue planets endlessly drifting in darkness. But what if a passing star were to snatch one up? In the grand ballet of the galaxy, stars sometimes act like cosmic fishermen, drawing stray planets into orbit. If a rogue planet happens to pass slow and close enough to a star, gravity can capture it. The condition is delicate. Too fast or too distant, it just flies by. Just right, it falls in. But given enough time and enough wanderers, such chances will occur. In effect, a star's gravity can reel in a wandering world, turning an interstellar drifter into one more member of the family. Surprisingly, our own sun is capable of this cosmic capture. Studies of stellar motions show that the sun's gravitational net extends extremely far. One analysis suggests the sun could have snared a Jupiter-sized rogue from nearly 4 light-years away, almost to the distance of our nearest neighbour, Alpha Centauri. In practical terms, stars and their neighbours can exchange planets like trading cards over eons. Even in our solar system, the distant Oort cloud could be filled with objects captured in the past. When the sun was young in a star cluster, passing siblings may have liberated or exchanged dozens of small worlds. We see an example of such capture in our own backyard. Neptune's largest moon, Triton, is a prime clue. It orbits backward around the planet, unlike any regular satellite. Astronomers conclude Triton was not born with Neptune, but was captured from the Kuiper belt long ago. If a planet the size of Pluto or Triton could be grabbed by Neptune, why not an entire rogue planet by a star? The dynamics are the same. A wandering world drawn into a system could settle into a wide, eccentric orbit if it loses enough kinetic energy. But what happens after capture? A newly acquired rogue would probably end up on the distant fringes of the system. It could end up circling its new star at dozens of thousands of astronomical units, thousands of times farther than Earth orbits. In that chill, outer orbit, it might spend eons, barely warmed by the faint starlight. Over time, however, the tug of other planets or passing stars could slowly shrink its path. On rare occasions, it might sink closer. If a captured rogue ever ventures inward sufficiently, the star's warmth could finally melt its ice. Imagine the scene. After millions of years of darkness, the sky brightens with a star's glow, and icy plains begin to thaw. For the first time in memory, the planet experiences a dawn. Such a capture could radically change the rogue world's destiny. If any life had developed in eternal night, exposure to sunlight would be shocking. Suddenly, new energy and possibilities would flood the environment. Aquatic habitats might expand toward the sunlit surface, or long-frozen ecosystems could find new nutrients. Even without life, the thaw could create spectacular geologic activity. Ice sheets cracking, seas flowing, volcanic outgassing. In a sense, the planet would get a second chance at being a daylight world, its frozen history giving way to a new chapter. Thus, the tale of these wandering planets comes full circle. A world born around one star, cast into the void, could one day fall into another star's embrace. The boundaries between star systems are not absolute. Some rogue planets, once thought lost forever, may be captured by wandering stars and become long-term residents of new systems. Even if rare, these events remind us how dynamic the cosmos is. Our exploration of rogue worlds is far from over. Each discovery will continue to challenge our ideas of life, home, and the eternal dance of planets and stars. As the odyssey of wandering worlds continued, the twilight of space seemed to cloak these hidden travelers in deeper mystery. The story had unfolded across lightless gulfs and ancient nights, yet curiosity remained a constant companion. In the quiet of interstellar space, hope and wonder mingled with questions that had yet to find answers. Now the journey pressed into techniques that allowed astronomers to sense objects too faint to see, objects whose gravity gave them away in transient glimmers. The method, at the heart of this part of the narrative, involves light, bending, under gravity's gentle persuasion. When a massive object passes in front of a distant star, its gravity acts like a lens, magnifying and distorting the background starlight and producing a luminous arc called an Einstein ring. If a rogue planet lies near the path of light, it adds a brief spike to the brightness curve, betraying its presence. This event, known as gravitational microlensing, lasts for a short period of time, often weeks, and the brightness returns to normal once the alignment passes. To sense the fleeting whisper of such events, astronomers watch millions of stars in the crowded heart of the Milky Way, waiting for the rare moment when a lensing star and a background star align. Microlensing is the only technique that allows discovery of planets thousands of light years away, far beyond the reach of radial velocity or transit methods. It can detect planets too small or too distant to influence their star's motion or block their light. This makes microlensing particularly suited to find free-floating worlds whose only signature is the gravitational warping of light. Unlike other exoplanet techniques, a microlensing event is a one-time encounter that cannot be repeated. The alignment that causes the lensing is unique, and once it has ended, the event is gone forever. The observer cannot revisit the same configuration to measure the planet again, which makes detailed characterization challenging. Distances and masses must be inferred from the shape of the light curve, and often suffer large uncertainties, leaving open questions about how far away the lensing planet really is. Despite these challenges, the method has distinct advantages. It is sensitive to planets at moderate distances from their stars, and even to planets not bound to any star. Microlensing can detect Earth mass objects, as well as giants, because the gravitational signature depends on mass, but not on light. It allows astronomers to probe a huge volume of space, reaching into the densely packed central bulge of the galaxy, where millions of stars crowd into the view. To find these transients, teams such as the optical gravitational lensing experiment and the microlensing observations in astrophysics survey, monitor hundreds of millions of stars, and alert follow-up telescopes when a candidate event is detected. As many as 500 microlensing events per year are reported, yet only a small fraction reveal planets. The difference between a lensing event caused by a star alone and one with a planet lies in subtle distortions that require careful modeling. Gravity acts like an artist, tracing curves of light that encode mass and distance. When the lensing star has a planet, the light curve displays a sudden spike or dip, depending on the planet's position relative to the line of sight. Astronomers fit models to these curves to estimate the planet's mass and separation. But degeneracies often arise, making it difficult to distinguish between a low-mass planet close to its host and a higher-mass planet farther out. For rogue planets with no host star, the curve simplifies, yet the absence of a luminous companion also complicates distance estimation. The detective work of measuring a rogue planet's mass often comes down to parallax. Observers at different positions in the solar system record the same microlensing event, and the slight difference in timing and magnification reveals the lens's distance and hence its mass. A proposed mission, conceptually named after the queen who led an Egyptian fleet, plans to place a small telescope on a spacecraft bound for Mars. By observing microlensing events simultaneously from Mars and Earth, Scientists could measure the parallax and break the degeneracy between mass and distance. This mission would rely on artificial intelligence to sift through the torrent of data, because only a tiny fraction of the monitored stars will undergo microlensing at any given time. An onboard algorithm would process photometric measurements and identify candidate events in real time. Only the most promising events would be sent back to Earth for detailed analysis, conserving bandwidth. Such autonomy would allow the mission to sample more events and to catch rare, short-duration events that could reveal low-mass rogue planets. Artificial intelligence can recognize patterns within the noise of starlight, flagging minute deviations that might otherwise escape notice. The algorithm would learn from thousands of simulated microlensing curves, training to distinguish planetary signals from instrumental noise and variable stars. When it identifies an event, the spacecraft would send a compressed data packet and coordinates, enabling ground-based telescopes to join the observation and provide additional measurements. In this way, technology becomes an active participant in the cosmic hunt. Determining the mass of a free-floating planet is more than an academic exercise. Mass is the fundamental parameter that shapes a world's evolution, its ability to retain heat, its atmospheric chemistry, and its potential to harbour moons. Knowing whether a detected rogue is Earth mass or Jupiter mass informs theories about how such objects are born. A distribution of masses across many rogue planets would allow astronomers to test whether they form like stars through collapse or like planets through ejection. The rarity of microlensing events is partly offset by the fact that a single microlensing survey can probe millions of stars. Yet this rarity is also why confirmed detections remain few. A rogue planet detection occurs only when a planet crosses the line of sight to a star and Earth happens to be watching. If the alignment is slightly off, the gravitational lensing is too weak to notice. Thus, astronomers must be patient, combing through years of data for those brief and fortuitous alignments. Even when a microlensing event reveals a promising candidate, confirmation demands persistence. Without a host star, there is no telltale stellar motion to measure, and no eclipse to observe again. To rule out the possibility that the lensing object is a distant star or a binary, astronomers turn to archival images taken long before and long after the event, searching for any luminous companion near the lensing position. If the images show no star brighter than a certain limit, the candidate remains a leading rogue planet suspect. In one celebrated case, a tiny microlensing event lasted only 42 minutes, implying an object with a mass between Mars and Earth. Its short duration suggested that the lensing body was extremely small, and the curve lacked the features that would accompany a stellar companion. Ground-based surveys had caught the event in the nick of time. When astronomers searched for a host star near the lensing location, they found no star within about 8 astronomical units, supporting the idea that the object was free-floating. Such Earth mass or sub-Earth mass candidates are rare and represent the extreme sensitivity of microlensing. They reveal that not only giant planets may wander through interstellar space, but also objects the size of small rocky worlds. These tiny rogues might be remnants of disrupted planetary systems, or the failed embryos of star formation. Confirming their nature often depends on follow-up observations with more sensitive instruments, which can search for faint host stars that ground-based telescopes cannot see. Another challenge arises when a microlensing event could also be caused by a planet bound to a very faint or distant star. Without direct detection of the host, the distinction between a truly free-floating planet and a widely separated planet with an unseen star is blurred. Astronomers sometimes refer to these objects as isolated or loosely bound, rather than strictly free-floating. Future telescopes with infrared sensitivity may detect red dwarf hosts even when they are invisible in optical images. One rogue candidate discovered through microlensing showed a brief spike in brightness, consistent with a planet of several Jupiter masses. Archival images from a space telescope taken decades earlier were examined to search for any luminous companion. The absence of a star, down to a certain magnitude limit, strengthened the free-floating interpretation, though the possibility of a faint red dwarf remained. This case illustrates how independent lines of evidence must converge to confirm a rogue planet. As technology advances, the difficulty of confirmation will gradually recede. Infrared observatories can peer through dust and detect cool stars that optical telescopes miss. Combined with precise astrometry, they can reveal subtle motions that betray the presence of a faint host star. Confirming a rogue planet becomes a matter of elimination, showing that no plausible host exists within reasonable distance, and that the mass inferred from microlensing must belong to a solitary body. While current surveys rely on networks of ground-based telescopes, future missions will carry microlensing into space. A planned space observatory will conduct a dedicated survey of the galactic bulge, scanning hundreds of millions of stars and recording light curves with exquisite precision. Equipped with a wide field of view and sensitive detectors, this mission is expected to detect hundreds to thousands of free-floating planets, providing the first statistical census of these worlds. Its observations will complement ground-based efforts by adding continuous, uninterrupted data and improved sensitivity to low-mass planets. The census will shed light on the number of rogue planets in the Milky Way. Some estimates suggest that they could number in the billions, possibly outnumbering the stars themselves. If even a fraction of these bodies are detected, astronomers will finally have enough examples to map a mass distribution and test theoretical models of their origin. Are large rogues rare because giant planets are less likely to be ejected, or are small rogues more common because planetary systems produce many embryos? The survey aims to answer these questions. This future telescope will not work alone. Ground-based facilities and other space observatories will join the campaign, forming a network that catches and characterizes microlensing events from multiple angles. Observatories in different orbits can provide parallax measurements, helping to determine distances and masses. Combining data from widely separated platforms yields a three-dimensional view of the event, breaking degeneracies and refining the properties of the lensing object. The contributions of this mission extend beyond statistics. For each detected rogue planet, the light curve and parallax measurement will provide an individual mass and distance. Combining these with models of the galaxy's structure can reveal the distribution of free-floating planets across the disk and bulge. Trends may emerge, such as whether rogues are more common in dense stellar environments where gravitational interactions are frequent. The result will be a map of wandering worlds, etched by gravity's imprint on starlight. Another powerful eye in the sky, already operational, brings its own strengths to the hunt. A space-based infrared observatory has recently captured images of free-floating planets in star-forming regions by direct imaging. These objects are young, luminous, and still hot from formation, shining dimly in the infrared. Among them, 6 candidates were found in a cluster of gas and dust, with masses between 5 and 10 times that of Jupiter. Surprisingly, one of these massive rogues shows signs of a circumplanetary disk, a swirling halo of dust reminiscent of the disks around young stars. The disk hints at a mini-planetary system in the making. The discovery of silicate grains and warm dust around free-floating planets suggests that the building blocks of moons and planets can assemble even without a stellar host. The mass and structure of these disks are scaled down. Like miniature versions of protoplanetary disks around stars. The lightest planet in the sample, with mass comparable to several Jupiters, shows a particularly rich disk, raising the possibility that satellites could form in its embrace. The existence of disks around free-floating giants rekindles the debate about their origins. Massive objects, 5 to 10 times Jupiter's mass, may form like stars through the collapse of a gas cloud. In this scenario, they are brown dwarfs or planetary mass fragments of star formation, born independently and later ejected or isolated. The presence of disks supports this view because circumstellar disks are a natural byproduct of cloud collapse. On the other hand, smaller rogues could be planets expelled from their host systems by gravitational interactions. If a rogue planet forms in a protoplanetary disk around a star and is later ejected, its satellites would have formed in the circumstellar environment and may remain bound after ejection. The ejection process could rip away smaller moons and debris, but larger satellites might survive, creating a planetary system adrift in interstellar space. Alternatively, if the rogue is a collapsed fragment, its own disk could spawn satellites that orbit it like moons. In both cases, miniature systems provide laboratories for studying planet and satellite formation under conditions devoid of stellar radiation. The classification of such satellites can be ambiguous. If a moon orbits a rogue planet that is itself free-floating, does the secondary body count as a planet or a moon? Astronomers grapple with definitions, but the underlying physics is clear. Gravitationally bound structures can form and persist around isolated planets. Researchers have noted that the building blocks of planets are present around objects barely larger than Jupiter, implying that scaled-down versions of planetary systems could exist, reduced in mass and size by factors of 100 or more. Returning to the question of origins, we find that ejection is one of several pathways for a planet to become rogue. In the chaotic early stages of a planetary system's life, gravitational encounters can fling planets outward. A giant planet may scatter a smaller neighbor, or a passing star could destabilize orbits, sending a planet into interstellar space. Over the course of billions of years, such interactions may produce a population of free-floating bodies that drift between the stars. These processes might be common in dense clusters and rarer in isolated systems, shaping the distribution of rogues across the galaxy. Another path involves the violent death of a host star. When a massive star explodes as a supernova, the sudden loss of mass can unbind the orbits of its planets, hurling them into space. The newborn neutron star, or black hole, may retain some companions, but those at larger distances may escape entirely. Likewise, planetary orbits around stars in binary systems can be disrupted when one star evolves into a giant and loses mass. These events, while less common than ejection by planetary scattering, contribute to the diversity of rogue planet origins. The idea that some free-floating objects might never have had a host star raises fascinating possibilities. If giant rogues form like stars, then star formation can produce a continuum of masses from large stars down to objects only a few times the mass of Jupiter. This continuum blurs the line between planets and brown dwarfs and suggests that the same physics governs the collapse of molecular clouds across a wide range of scales. These objects would wander the galaxy as independent entities, retaining their own disks and perhaps forming satellites. Observationally, distinguishing between ejected planets and star-like objects can be difficult. For giant rogues, the presence of a circumplanetary disk may indicate star-like formation, whereas the absence of a disk and the presence of heavy metals may suggest planetary origins. For small rogues, the timescales of microlensing events and the inferred masses provide clues. Ultimately, a combination of mass measurements, chemical fingerprints, and dynamical modeling will help classify the origins of individual rogue planets. The extremes of the rogue population offer glimpses into the boundaries of planetary physics. In a dark patch of sky about 420 light-years away, astronomers painstakingly combined 20 years of data from multiple telescopes to identify at least 70 starless worlds. The sample could contain up to 170 such objects, representing the largest single haul of free-floating planet candidates to date. These bodies range in mass from several times Jupiter to perhaps around the deuterium burning limit, and some may be very low-mass brown dwarfs. The method used to find this trove did not rely on microlensing, but on measuring proper motions and colours. By comparing images taken years apart, scientists traced the tiny motions of faint objects across the sky and distinguished them from background stars. Those that moved with the local star-forming region but lacked a bright host were flagged as rogue candidates. Combining data from space and ground allowed the team to filter out contaminants and compile a catalogue that more than doubled the number of known rogue planet candidates. Discoveries like this one show that the census of rogues is only beginning. If a patch of sky can yield dozens of candidates, then the galaxy at large may harbour millions. The density of starless worlds may be highest in regions where star formation has recently occurred, because the ejection of planets or the fragmentation of clouds might produce many isolated objects. As surveys extend to other regions, the variation in rogue planet density will become clearer, revealing the environmental dependence of their formation. At the other extreme lies the smallest rogue planet candidate. The microlensing event that betrayed this object lasted less than an hour, shorter than any known planetary microlensing event. Modelling indicated a lensing body with a mass between that of Mars and Earth, making it the lightest free-floating exoplanet detected. Its fleeting signal underscores the challenge of catching such tiny objects, as the required alignment is precise and the time window narrow. In terms of extremes, we also find free-floating planets that may have unusual compositions or physical conditions. Some simulations suggest that rogue planets, free from stellar radiation, might retain thick atmospheres and internal heat that keep subsurface oceans liquid for billions of years. Others might be icy husks with surfaces frozen solid. The variety in mass, composition, and thermal state across the rogue population broadens our conception of what constitutes a planet and invites speculation about potential niches for life. The record-breaking discoveries not only excite the imagination, but also push the limits of existing models. Each new rogue planet candidate challenges astronomers to refine detection methods, improve models of gravitational lensing, and consider alternative formation pathways. The largest sample may reveal a peak in the mass distribution. The smallest may test detection sensitivity. Outliers anchor the extremes of the population and define the boundaries of what is possible in planetary systems. Building a comprehensive census of rogue planets requires patience and collaboration. Different detection methods complement each other. Microlensing excels at finding distant and low-mass objects, while proper motion surveys catch nearby and massive objects. Infrared imaging reveals young, luminous rogues in star-forming regions. Combining these techniques allows astronomers to sample the rogue planet population across ages, masses, and environments. The Galactic Bulge Time Domain Survey, planned for the Future Space Telescope, will provide a statistically significant sample of microlensing events. Within this dataset, hundreds to thousands of rogue planets may be identified, enabling scientists to estimate their abundance relative to stars. This will be the first time that free-floating planets are studied not as rare curiosities, but as a population with measurable properties and distributions. The survey will help determine whether rogue planets outnumber bound planets, or whether they are a minority product of dynamical chaos. As the census grows, it will inform models of planetary system evolution. If rogue planets are found to be abundant, then ejection must be a common outcome of planet formation. The dynamical histories of many star systems would include periods of violent scattering. If, on the other hand, rogue planets are rare, then systems may generally remain stable, and the formation of star-like planetary mass objects may be limited. The census will thus feed back into our understanding of how solar systems like our own form and evolve. Mapping the distribution of rogue planets also touches on the architecture of our galaxy. If they cluster toward the galactic center, it could indicate that the dense environment there promotes their creation through gravitational interactions. If they are uniformly distributed, it might suggest that star formation processes produce free-floating objects everywhere. Should a gradient with distance from the galactic plane emerge, it could reflect differences in star formation history and dynamical heating. Each pattern will carry clues to the interplay between planets and their environment. The census will help determine the mass function of free-floating planets, a relationship that describes how many planets exist at each mass. This mass function is a critical test of theoretical models. A steep rise toward low masses would imply that small planets are readily ejected or formed in isolation, while a flatter distribution might mean that only large planets or brown dwarfs are produced in large numbers. Comparing the mass function of rogue planets with that of bound planets may reveal whether different processes dominate in each case. Beyond numbers and distributions, the census will illuminate the diversity of planetary architectures. Some rogue planets may carry rings and moons. Others may host atmospheres of hydrogen and helium, or be stripped down to rocky cores. Observations of disks around free-floating giants imply that satellite systems can form independent of stars. The census may reveal how common such mini-systems are, and whether they resemble scaled-down versions of solar systems, or follow different patterns. In time, the census could help identify targets for future exploration. Although interstellar travel remains far beyond our capabilities, free-floating planets with large moons or thick atmospheres could one day be destinations for robotic probes launched across tens of thousands of years. The detection of a rogue planet within a few hundred light-years might inspire plans for advanced propulsion systems to reach it. Even if such voyages are centuries away, the knowledge that planets wander between the stars invites us to imagine new horizons. Our perspective on the cosmos shifts when we consider the sheer number of planets not bound to stars. The night sky becomes more than a field of points. It becomes a sea of worlds drifting unseen through dark space. The line between solar systems and the interstellar medium blurs, with planetary bodies occupying the voids between stars. This population challenges our understanding of planetary formation and broadens the concept of planetary neighborhoods. Astronomers have long wondered whether free-floating planets could host life. Without starlight, the surface of such a world would receive little heat. Yet internal sources such as radioactive decay and residual heat from formation could keep an ocean beneath an insulating shell of ice liquid for billions of years. A thick atmosphere could trap geothermal heat, creating a temperate environment at the surface. The potential for subsurface oceans or warm niches on rogue planets hints at the possibility of life even in deep space, an idea both haunting and inspiring. The detection of mini-planetary systems around free-floating giants raises the possibility that moons could harbour environments more hospitable than the planet itself. A large rogue could host several moons, each with its own geology and potential for subsurface water. Tidal heating, generated by gravitational interactions between the moons and the planet, could warm the interiors and fuel geological activity. Such systems might be tiny analogues of Jupiter and its Galilean moons, offering shelter in the cold of interstellar space. The puzzle of origins is intimately tied to the puzzle of destiny. If free-floating planets can form their own satellite systems, then starless worlds could propagate complexity throughout the galaxy. The ejection of planets could be a mechanism by which life or its precursors are dispersed. Conversely, if star-like collapse produces the majority of rogue planets, then these worlds represent a continuum of star formation rather than a product of planetary system instability. Each scenario paints a different picture of how common planetary systems may be in the galaxy and how life might migrate between them. Building the census will require not only advanced telescopes, but also collaboration among observers, theorists, and data scientists. Machine learning algorithms will sift through terabytes of photometric data, identifying microlensing events and distinguishing them from variable stars. Theorists will model light curves, simulate ejection scenarios, and interpret mass distributions. Observers will coordinate follow-up campaigns, combining optical, infrared, and radio observations to rule out host stars and to measure parallax. The synergy between these efforts will accelerate progress. As the census grows, it will refine our understanding of star formation. If star-like collapse produces planetary mass objects in significant numbers, then the initial mass function of stars must extend into the planetary regime. This would have implications for the distribution of angular momentum, the rate of star formation, and the enrichment of the interstellar medium. Conversely, if ejection dominates, then the interactions among planets and stars in young systems shape the eventual architecture of those systems. The census will thus inform both stellar and planetary astrophysics. Some of the most important insights may come from comparing the properties of rogue planets across different galactic environments, the distribution of masses, the presence or absence of disks, and the frequency of moons could vary depending on the density of surrounding stars, the metallicity of the interstellar medium, or the history of star formation. By sampling multiple regions, from the galactic bulge to the disk and halo, astronomers can discern trends that reveal the influence of environment on the free-floating population. The upcoming space mission is poised to revolutionize this field. With its sensitive detectors and wide field of view, it will watch the central bulge of the Milky Way continuously for months, recording subtle variations in the brightness of millions of stars. Its data will be shared with ground-based observatories and analyzed by scientists worldwide. The mission's goal is not only to find rogue planets, but also to determine how common they are and what masses they typically have. Success will depend on careful calibration and thorough analysis. The mission's design includes a microlensing survey that will also detect bound exoplanets, brown dwarfs, and stellar binaries. This comprehensive dataset will allow comparisons between free-floating and bound objects, providing insights into the processes that produce them. By capturing the full range of gravitational lenses in the crowded bulge, the mission will build a rich catalogue that can be mined for years to come. Each light curve is a piece of cosmic music, telling the story of a lens and its companions. Looking even further ahead, concept missions to outer planets or interstellar space could provide new baselines for microlensing parallax measurements. A spacecraft trailing Earth or leading it by millions of kilometers would observe microlensing events from a different perspective. The timing differences between detectors separated by such distances could yield precise measurements of lens masses and distances. With enough such baselines, astronomers might even detect the slow drift of free-floating planets across the sky over years or decades. On the theoretical side, models of planetary system dynamics will evolve in response to the census. Simulations of planet formation and evolution will incorporate the observed frequency and mass distribution of rogue planets. These models will explore how often planets are ejected, under what circumstances, and what types of systems produce ejected bodies. They will also examine the interplay between star formation and rogue planet formation, testing whether fragmenting clouds produce planetary mass objects at the same rate as larger stars. Public engagement will be a vital part of this endeavour. The idea of planets adrift in interstellar space captures the imagination, inspiring awe at the notion of worlds lost between stars. Citizen science projects could invite the public to examine light curves and help identify microlensing events. Educational programs can use the concept of rogue planets to teach about gravity, planetary formation, and the scale of the universe. The narrative of wandering worlds resonates with people's fascination for journeys and exploration. Artists and writers may find inspiration in the idea of a planet floating through the cosmic night. Stories of lonely worlds, frozen oceans, and potential hidden life can be woven into art and literature. The factual basis provided by scientific research grounds such creativity, while imagination fills the gaps. The interplay between science and art enriches our culture and fosters a deeper appreciation for the mysteries of the universe. As new data pours in, patterns may emerge that challenge existing theories. Perhaps rogue planets are most common in metal-poor regions, suggesting that star formation processes in such environments favour the production of isolated objects. Perhaps a surprising number of free-floating planets host disks and moons, indicating that planet formation can occur outside of stellar systems. Or perhaps the mass distribution is bimodal, with peaks at small and large masses, hinting at two distinct formation channels. Each possibility will spur further investigation. The detection of rogue planets also intersects with the study of dark matter. Microlensing surveys sensitive to planetary masses could, in principle, detect primordial black holes or other exotic compact objects if they exist in certain mass ranges. Distinguishing between a planet and a black hole lensing event may not always be possible without additional information. Thus, the techniques developed for rogue planet detection could contribute to the broader quest to understand the dark components of the universe. When considering the future, it is instructive to reflect on how far the field has come. Only a few decades ago, planets beyond the solar system were purely speculative, and the idea of planets not bound to stars was the realm of science fiction. The first microlensing detections of exoplanets provided proof of concept. With each new generation of surveys, the sensitivity improved, and the first free-floating planet candidates were announced. Today, a growing list of confirmed and candidate rogues hints at a vast unseen population. The progress is a testament to human curiosity and the power of collaboration. Observatories in different countries share data. Archives preserve images for decades. Algorithms developed for one purpose find applications in another. Each detection builds upon the work of countless people, from engineers who design instruments to observers who monitor the sky and analysts who parse data. The community of planetary scientists, astronomers, and citizens together weaves the tapestry of discovery. As we look to the horizon of possibility, we recognize that free-floating planets are only one part of the cosmos's hidden richness. They remind us that there are worlds and phenomena beyond the comfortable realm of stars and planets orbiting them. There are gravitational interactions that fling planets into the void and star-forming processes that create solitary objects. The universe is full of surprises, and each new window we open reveals a landscape more complex than we imagined. The narrative of rogue planets thus continues, flowing from detection techniques through challenges of confirmation into a future of powerful telescopes and theoretical insights. The search will not end with a single mission or survey. Rather, it will evolve as new instruments and ideas emerge. The field will grow in parallel with our capacity to detect subtle signals and our willingness to explore the farthest reaches of the cosmos. In this way, the story of these wandering worlds becomes a part of the larger human quest to understand our place in the universe. What draws us to these invisible travelers is perhaps a reflection of our own sense of journey. Humans, too, are wanderers, moving across a cosmic landscape on a planet that is itself orbiting a star in a galaxy drifting through space. The knowledge that there are planets without stars evokes both a feeling of isolation and a connection to a broader universe. It invites contemplation of the resilience of life and the adaptability of physical processes under different conditions. As the chapters of exploration unfold, they build upon one another. The detection methods show us where to look. The confirmation techniques teach us caution. The missions on the horizon promise new data. The theories of origin challenge us to reconsider what a planet is. The extremes broaden our sense of possibility, and the census grounds our dreams in numbers. Each element interlaces with the others, forming a tapestry of knowledge and curiosity. The slow pace of the narrative mirrors the pace of research. Years pass between the identification of a microlensing event and the final publication confirming a rogue planet. Decades of observations accumulate to yield a single outlier. The march of technology and the accumulation of data move forward steadily, like the gentle drift of a planet through interstellar space. Patience becomes a virtue for scientists and storytellers alike. In the background, there is a constant interplay between what is known and what remains unknown. Some questions have been answered. We know that rogue planets exist, that they come in a range of masses, and that some host disks. Other questions persist. How many are there? How do they form? Do they have moons and atmospheres? Do they host life? Each answer leads to new questions, and the cycle continues. As this part of the journey draws to a pause, the narrative leaves the listener not with a conclusion, but with an invitation. The next segments will delve further into the implications of the rogue planet census, the philosophical considerations of worlds without stars, and the emergent technologies that will expand our reach. The story, like the planets it describes, continues onward without end, drifting through the endless night toward horizons yet unseen. Deep within the realm of gravity's influence lies a subtlety of microlensing that deserves attention. When light grazes a mass, it follows the curvature of space-time, and the path depends on both the mass of the lens and the geometry of the alignment. In microlensing, the lens is typically a star or planet, and the bending is tiny, producing magnifications that are modest compared to those seen in galaxy-scale lenses. The scale of the lensing is characterized by the Einstein radius, a distance determined by the mass of the lens and the distances to the observer and the source. This radius defines the region where the bending of light creates a symmetric ring in ideal alignments and sets the timescale of the event. The timescale of a microlensing event is proportional to the Einstein radius, divided by the relative velocity of the lensing object and the line of sight. For a planet of Earth's mass, the typical Einstein radius is so small that the event lasts only minutes or hours. For a Jupiter-mass planet, the radius is larger, and the event can last days or weeks. Understanding these timescales allows observers to tailor their surveys to capture short and long events. High-cadence photometry is essential, as sampling gaps could miss rapid spikes or dips in brightness that indicate planetary signals. The relationship between the Einstein radius and mass also means that microlensing is more sensitive to massive planets. For low-mass objects, the small radius leads to faint and brief signals that can be lost in noise. Surveys address this by increasing the frequency of observations and by using larger telescopes to achieve better signal-to-noise ratios. Machine learning algorithms can also be trained to pick out subtle features in the light curves, enhancing the probability of detecting low-mass rogues. As technology improves, detection thresholds will push toward even smaller masses. Historically, the concept of gravitational lensing was predicted by Einstein, but considered unobservable due to the precision required. It was only in the latter half of the 20th century that astronomers began to detect strong lensing by galaxies and clusters. The shift to microlensing for exoplanets emerged from the realization that stars could act as tiny lenses. Early experiments showed that microlensing events occurred and that they could be used to detect dark objects such as black holes or faint stars. With the advent of sensitive digital detectors and global networks of telescopes, the microlensing technique blossomed into a powerful tool for planet hunting. Instrumental advances have played a crucial role. Early microlensing surveys relied on photographic plates and small fields of view, limiting their sensitivity. Modern detectors with large mosaics of CCDs can monitor millions of stars simultaneously. Automated pipelines process images in real time, subtracting reference images to highlight variability. Artificial intelligence helps distinguish lensing events from variable stars and noise. The synergy between hardware and software has transformed microlensing from a niche field into a mainstream exoplanet discovery method. Another nuance lies in the blending of light from multiple sources. In crowded fields like the galactic bulge, starlight from the lens, the source, and unrelated nearby stars can blend together, complicating the light curve. Blending can diminish the apparent magnification and distort the event shape. Accurate modeling must account for blended light to avoid underestimating the lens mass. High-resolution follow-up imaging helps disentangle blended sources and refine the parameters of the event. A deep understanding of blending effects is essential for microlensing surveys, ensuring that subtle lensing signals are not lost in a sea of overlapping starlight. As datasets grow and observations become more precise, improved deblending techniques will unlock more discoveries and refine existing measurements, pushing the boundaries of what microlensing can reveal. Ground-based microlensing surveys often contend with weather, daylight, and the rotation of the Earth, which create gaps in the light curves. Networks of telescopes distributed across longitude mitigate this by providing continuous coverage. When one observatory is in daylight or under clouds, another can take over. Space-based observatories eliminate atmospheric limitations and can observe continuously, offering more complete light curves. The combination of space and ground observations yields the best of both worlds, providing wide coverage and high precision. Even with robust coverage, degeneracies can plague interpretations. For instance, a single planet can produce multiple possible models that fit the data equally well, differing in mass or separation. Additional information, such as parallax or the finite source effect, can break these degeneracies. The finite source effect occurs when the background star has a measurable angular size relative to the Einstein ring, adding features to the light curve that depend on the relative motion. Detecting this effect requires high precision, but provides extra leverage to infer lens properties. Another way to break degeneracies is to observe the same microlensing event from two locations separated by thousands of kilometers. Parallax measurements compare the timing of the event and the apparent magnification differences between observatories. The larger the baseline, the more pronounced the parallax effect. A spacecraft in solar orbit provides an ideal baseline relative to Earth-based telescopes. Concept missions like the one envisioned to piggyback on a Mars-bound mission show how future exploration could double as a lensing observatory. The AI algorithms designed for microlensing surveys are part of a broader trend in astronomy. Machine learning aids in classification, pattern recognition, and anomaly detection across datasets. In microlensing, the challenge is to identify rare events amidst a sea of variability. Networks are trained on simulated light curves and real data, learning to ignore common variable star patterns and instrumental glitches. By flagging potential events in real time, AI allows human observers to focus on the most promising signals and allocate resources efficiently. Training data for these algorithms must encompass the diversity of microlensing events, including those with multiple planets, binary lenses, and finite source effects. This requires large libraries of synthetic light curves generated by Monte Carlo simulations. Researchers vary parameters such as mass ratios, separations, source sizes, and trajectories to create realistic scenarios. The resulting models feed into networks that learn to recognize the telltale features of planetary lensing. As the real dataset grows, the algorithms are continually refined, improving performance. Beyond detection, AI can assist in parameter estimation. Traditionally, fitting microlensing light curves involved manual adjustment of model parameters and computationally expensive searches of parameter space. Machine learning techniques such as neural networks and Gaussian processes can approximate the mapping between light curves and physical parameters. These approaches can produce quick estimates that serve as starting points for more precise modeling. The combination of AI and traditional analysis accelerates the interpretation of events and enables rapid response to interesting discoveries. In the realm of space-based microlensing, the design of instruments is tailored to capture faint variations. Detectors must be sensitive across a broad range of wavelengths to account for the red colors of stars in the galactic bulge. The optics must be stable, with minimal jitter, to avoid introducing artificial variability. Data storage and downlink capacity must handle continuous monitoring of millions of stars. Engineers work to balance field of view, pixel scale, and photometric precision to optimize for microlensing science. The scheduling of observations during the microlensing survey is crucial. The survey must observe fields near the galactic center for extended periods during times when that region is visible to the telescope. For a space mission in Earth orbit, this may mean pointing near the Sun and managing stray light. For a mission at Lagrange points or in heliocentric orbit, the geometry is different, offering more flexibility. Mission planners simulate various pointing strategies to maximize event detection rates while maintaining spacecraft safety and thermal constraints. One of the goals of the upcoming survey is to measure the free-floating mass function, which describes how the number of free-floating planets varies with mass. This function is analogous to the initial mass function for stars and brown dwarfs. To determine it, astronomers must account for detection efficiencies and biases. Smaller planets are harder to detect, and events with certain geometries may be missed. Statistical techniques, including Bayesian methods and population synthesis, are used to correct for these biases and to infer the underlying distribution from the observed sample. The outcome will inform theoretical models. For example, a steep mass function dominated by Earth mass objects would suggest that low-mass planets are frequently ejected, perhaps because they are easily perturbed by giant neighbors. A mass function dominated by Jupiter mass rogues would point to star-like formation or to violent scattering events that involve massive bodies. Intermediate forms could indicate a mixture of ejection and in situ formation. Comparing the free-floating mass function to that of bound exoplanets may reveal subtle differences that reflect their divergent histories. Astrophysical simulations of planetary system formation and evolution provide context for these observations. In some models, planets form through the accretion of solid cores, followed by gas accretion. If multiple giants form and migrate inward, gravitational interactions can destabilize their orbits, leading to ejection. The rate of ejection depends on the number of planets, their masses, and the properties of the protoplanetary disk. Other models show that planets can be ejected by passing stars in young clusters, especially if the cluster is dense and long-lived. Simulations strive to match the observed fraction of free-floating planets and test various initial conditions. The environment plays a crucial role. In dense star clusters, close encounters between stars can perturb planetary systems, increasing the likelihood of ejection. As clusters dissolve over time, ejected planets remain in the galactic field, adding to the rogue population. In contrast, isolated stars in sparse regions experience fewer interactions, and their planets are more likely to remain bound. By comparing rogue planet densities in different environments, astronomers can infer the importance of external perturbations. Metallicity, the abundance of elements heavier than helium, influences planet formation and potentially the production of rogues. High metallicity environments favor the formation of giant planets, which may then scatter smaller companions more readily. Low metallicity environments may produce fewer giants and hence fewer ejection events. Observing how the rogue population varies with metallicity across the galaxy can help connect planet formation to galactic chemical evolution. Microlensing surveys may detect statistical trends linking lens properties to the metallicity of the surrounding stellar population. Another aspect of environment is the age of the planetary system. Young systems may still contain remnants of planet formation, and the gravitational interactions among planets are more intense. As systems age, their orbits may settle into stable configurations. Rogue planet production may thus be front-loaded, occurring within the first 100 million years. Alternatively, later events such as stellar evolution or close encounters may eject planets at much older ages. Observing the ages of host stars near microlensing events could hint at when ejection is most prevalent. The interplay between rogue planets and life is a topic of speculation. Subsurface oceans on rogue planets could be heated by the decay of radioactive elements and tidal forces from orbiting moons. If life arose early on such a world, it might persist under the ice, isolated from the external universe. Alternatively, life could be seeded onto a rogue planet through panspermia, hitching a ride on icy debris ejected from a habitable system. The prospects for life in these hidden habitats evoke images of dark, warm oceans teeming with microbial ecosystems. Studies of our own solar system provide analogies. Europa and Enceladus, moons of Jupiter and Saturn, host subsurface oceans heated by tidal forces and radioactive decay. These oceans remain liquid despite being far from the Sun. If similar moons orbit rogue gas giants, their interiors could stay warm for billions of years. The absence of sunlight does not preclude life. Chemosynthetic organisms could thrive, utilizing chemical gradients as energy sources. Astrobiology thus broadens its canvas to include starless worlds as potential niches. Science fiction has long imagined planets without suns. Some stories depict frozen wastelands, while others envision self-luminous planets, heated internally or by exotic means. The reality, as revealed by science, is both stranger and more plausible. These worlds could be dimly lit by bioluminescent organisms or by faint auroras generated by magnetic fields. They might host ecosystems confined to warm oases around hydrothermal vents. The atmospheric composition of a rogue planet would be shaped by internal outgassing, lacking the photochemistry driven by stellar radiation. In addition to rogue planets, there may be rogue moons and dwarf planets. When planets are ejected, their moons may remain bound, or may themselves be torn away. A moon ejected with its parent becomes part of the same mini-system. A moon torn free could become an independent wanderer, perhaps colliding with other objects, or settling into a distant orbit around another star. The diversity of outcomes underscores the complexity of gravitational interactions and the richness of the rogue population. Some models suggest that planets can be captured into new systems. If a free-floating planet passes near a binary star or a system with a massive gas giant, it could lose energy and be gravitationally captured. The captured planet's orbit would be wide and eccentric, but it would become bound to a new host. Such captures may explain certain observed exoplanets with unusual orbits. In this sense, the journey of a rogue planet may not end in eternal isolation. It might find a new home. The potential for capturing rogue planets has implications for the habitability of planetary systems. A captured planet could bring its own moons and potentially its own biosphere. The injection of a new massive body could destabilize existing orbits, leading to further rearrangements. The dynamic history of a system thus influences not only its architecture, but also the prospects for life. Understanding capture mechanisms helps interpret observed exoplanet orbits and the diversity of planetary systems. Microlensing surveys might detect these captured planets if their orbits bring them in front of background stars. The light curves would reflect the mass and separation of the planet and its new host. Captured planets may have very large orbits, making them appear almost free-floating. Distinguishing them from true rogues would require parallax measurements and perhaps infrared detection of the host star. This highlights the importance of thorough follow-up observations and cross-matching between detection methods. The interplay with dark matter research offers another dimension. Microlensing surveys sensitive to planetary masses could detect black holes or exotic compact objects if they exist in the relevant mass range. Such objects would produce lensing events similar to those of rogue planets, but would have no possibility of a disk or associated moons. Distinguishing between a planetary mass black hole and a rogue planet requires additional information, such as the absence of infrared emission or the presence of relativistic effects. These possibilities remind us that gravitational lensing probes the full spectrum of compact objects in the universe. On cosmic timescales, the population of rogue planets may evolve. Early in the universe, star formation and the assembly of galaxies were more chaotic, perhaps leading to more ejections. Over billions of years, the frequency of ejection events may decline as planetary systems stabilize. Meanwhile, free-floating planets from early times might be captured by passing systems or might collide with interstellar debris. The dynamic interplay between formation, ejection, capture, and destruction shapes the evolving landscape of rogue planets over cosmic history. The eventual fate of a rogue planet is often to drift through interstellar space until it encounters another massive body. Encounters with stars are rare given the vastness of space, but over billions of years, a rogue planet may pass within a few hundred astronomical units of a star. In some cases, gravitational interactions could slow the planet and lead to capture. In others, the planet might pass unaffected. Understanding the frequency of such encounters informs our estimates of how many free-floating planets remain truly isolated versus those that find new homes. At the intersection of microlensing and astrometry lies another detection method. As a lensing object passes in front of a star, it not only magnifies the star's light, but also shifts its apparent position. This astrometric microlensing signal is tiny, but measurable with space-based interferometry. Detecting the astrometric shift allows a direct measurement of the lens mass and distance, complementing photometric microlensing. Future missions with astrometric precision on the order of microarcseconds could exploit this effect to detect and characterize rogue planets. The synergy between astrometric and photometric microlensing will be powerful. Photometric observations reveal the temporal evolution of brightness, while astrometric observations track the apparent motion of the source star. Combining these datasets breaks degeneracies and yields unique solutions for the lens mass, distance, and relative velocities. This multimodal approach exemplifies how diverse techniques can converge to provide a comprehensive picture of a single event. In this way, every detection becomes a window into the physics of gravity and planetary mass objects. As instruments become more sensitive, smaller mass objects come into reach. The detection of an object with mass comparable to Mars demonstrates that microlensing can probe the terrestrial regime. Pushing further could reveal even moon-mass bodies or large asteroids, though their lensing signals would be extremely brief. Detecting such tiny objects would challenge current techniques and require continuous, high-cadence monitoring by both ground and space telescopes. The prospect of discovering free-floating bodies as small as the Moon underscores the method's potential reach. The detection of a 42-minute microlensing event underscores the importance of rapid data sharing. When an event occurs, observers must react quickly to allocate telescopes and capture the peak. Real-time alerts and global communication networks ensure that events are not missed. Follow-up observations in different bands can constrain the source star's properties and detect potential anomalies. Such coordinated efforts require careful planning and robust infrastructure, reflecting the collaborative nature of modern astronomy. In the context of record-breaking rogue planet candidates, the discovery of a haul of over 70 objects stands out not only for its size, but also for its methodology. Measuring proper motion and color across decades of archival data demonstrates the value of long-term astronomical archives. What was once raw imagery becomes a treasure trove when re-examined with new algorithms and questions. This ability to mine historical data for new discoveries highlights the iterative nature of scientific progress. The proper motion technique also reveals the velocities of rogue planet candidates relative to their local environment. If an object shares the motion of nearby stars, it likely formed in the same region. If it has a distinctly different motion, it may be a visitor from elsewhere. Velocity measurements can hint at whether a rogue planet was ejected recently or long ago. The combination of motion, location, and mass allows astronomers to reconstruct possible histories for these wandering bodies. These histories can be complex. A planet might form in one star-forming region, be ejected early on, drift for millions of years, then pass near another region and be captured or perturbed. Its composition may reflect the metallicity of its birth site, providing clues to its origin. By analysing the chemical signatures of rogue planets detected by direct imaging or spectroscopy, astronomers could match them to known stellar populations. Thus, the investigation of rogue planets intersects with galactic archaeology, the study of how the Milky Way assembled over time. Spectroscopy of free-floating planets remains a frontier. Infrared spectra can reveal the presence of molecules such as methane, water vapor, ammonia, and carbon monoxide. These signatures depend on temperature and composition, which in turn depend on mass, age, and atmospheric processes. Young rogue planets are warm and luminous, making them easier to observe. Older rogues are colder and require sensitive instruments. Spectroscopy could test atmospheric models, constrain surface gravity, and even detect clouds or weather patterns on these solitary worlds. Weather on a rogue planet might be dominated by internal heat and rotational dynamics, rather than by stellar heating. In a gas giant, convection could drive storms and zonal winds, producing features analogous to Jupiter's Great Red Spot. In a terrestrial rogue, volcanic activity and cryovolcanism could create transient atmospheres and plumes. The absence of a star's ultraviolet radiation would alter atmospheric chemistry, perhaps leading to exotic compounds and long-lived gases. Observations of these phenomena would broaden the diversity of known planetary climates. Exchanging ideas between disciplines enriches the field. Planetary scientists studying the atmospheres of solar system bodies contribute insights into how atmospheres behave in low-temperature environments. Stellar astrophysicists offer models of star formation that inform the formation of brown dwarfs and rogue planets. Cosmologists bring perspectives on structure formation that set the context for the distribution of free-floating objects. The integration of these viewpoints reflects the inherently interdisciplinary nature of modern astrophysics. The cultural resonance of rogue planets may also influence public perception of science. Metaphors of wandering worlds can evoke feelings of isolation, resilience, or curiosity. They may serve as symbols in literature and art, reflecting human experiences of dislocation or exploration. Science communicators can harness these metaphors to engage audiences, illustrating complex concepts through relatable stories. In turn, the public's fascination can support funding and encourage students to pursue careers in science. Educational programs can use the concept of microlensing to teach mathematics and physics. Students can explore how the geometry of lensing leads to magnification, how curves are fitted to data, and how small variations reveal hidden objects. This hands-on approach can demystify abstract concepts and show the practical application of theoretical ideas. Moreover, the global collaboration inherent in microlensing surveys can serve as a lesson in teamwork and shared knowledge. The narrative of rogue planets also raises philosophical questions about definitions and classifications. What distinguishes a planet from a brown dwarf or a sub-brown dwarf? Does the presence of a disk or moons change an object's status? As the mass spectrum extends seamlessly from stars to planets, our categories may need to evolve. The International Astronomical Union may one day revisit the definitions of planets to account for objects that form like stars but have planetary masses. Such discussions reflect the dynamic nature of science, where new data prompt revisions of our frameworks. As the census grows, the sample size will allow more sophisticated statistical analyses. Scientists will apply techniques such as hierarchical Bayesian modeling to account for measurement uncertainties and selection biases. They will compare the observed mass distribution to predictions from population synthesis models. They will test whether the number of rogue planets per star correlates with properties such as stellar mass, metallicity, or age. These analyses will transform a collection of individual detections into a coherent picture of a cosmic population. The integration of data from multiple surveys will enhance reliability. Cross-matching microlensing detections with proper motion catalogues and direct imaging surveys can confirm candidates and identify duplicates. Combining data allows for the removal of false positives and the refinement of parameters. Meta-analyses will combine results from different teams, increasing statistical power and robustness. Such collaborations require standardized data formats and open sharing of results, exemplifying the collaborative spirit of astrophysics. Over time, the scientific community may compile an atlas of rogue planets. Each entry would include coordinates, mass estimate, detection method, environment, potential companions, and any peculiarities. This atlas would be a living document, updated as new detections and data arrive. It would serve as a resource for researchers and a source of wonder for the public. The act of cataloguing wandering worlds parallels the historical cataloguing of stars and galaxies, embedding free-floating planets into our cosmic map. The atlas will also feed into theoretical models. By comparing the spatial distribution of rogue planets with predictions from simulations, researchers can assess the accuracy of models. The atlas may reveal structures such as streams or clumps of rogue planets, hinting at past dynamical events. It may show a gradient in masses or a trend with galactic radius. Each pattern invites explanation and deepens our understanding of the galaxy's history. In the long term, the study of rogue planets may influence mission planning. If free-floating bodies are abundant in certain regions, spacecraft traveling through those areas may encounter them. Future interstellar probes could use rogue planets for gravitational slingshots or study them as waypoints. Knowledge of their distribution will inform navigation and hazard assessment. The presence of rogue planets may also be considered in the context of planetary defense, as a rogue could, in principle, enter the inner solar system. The contemplation of such possibilities underscores the connection between curiosity-driven research and practical considerations. While the primary motivation for studying rogue planets is scientific, the information gained could have unforeseen applications. History is rich with examples of fundamental research leading to technological or logistical advances. By exploring the unknown, humanity prepares itself for a future that may involve interactions with celestial objects beyond our current experience. As we extend our gaze into the interstellar void, we confront the reality that the universe is vast beyond comprehension. The light from distant stars travels for thousands of years before reaching us, and between those stars lie countless unseen objects. The detection of rogue planets reminds us that the dark spaces are not empty, but are populated by worlds we have yet to discover. This awareness adds depth to our appreciation of the cosmos and reveals a complexity that continues to unfold. The narrative of rogue planets thus intertwines with themes of exploration, uncertainty, and discovery. Each detection is both a scientific accomplishment and a reminder of the many unknowns that remain. The slow, deliberate accumulation of knowledge mirrors the gentle drift of the planets themselves. As we continue to watch, model, and interpret, we become participants in a cosmic dance choreographed by gravity and chance. The story will evolve, but the wonder it inspires will remain. There are still facets of gravitational microlensing that warrant deeper reflection. While microlensing relies on gravity-bending light, the bending also delays it, causing a slight time delay between different light paths. In large-scale lenses, such delays can amount to days. In microlensing, they are fractions of a second. However, this time delay encodes information about the gravitational potential and could, in principle, help differentiate between planets and other compact objects. Measuring such minute delays would require extreme precision, but represents an intriguing frontier for future technology. The shape of the lensing light curve is sensitive not just to the presence of a planet, but also to the planet's orbital motion. If the planet orbits its host star during the lensing event, its changing position can blur or split the signal. Orbital motion is often negligible during short events, but could be significant for long events involving wide orbits. Modeling such dynamical effects adds complexity, but also provides a way to infer orbital periods and orientations. In this sense, a microlensing light curve becomes a snapshot of a system in motion, capturing both mass and dynamics. In addition to planets and brown dwarfs, free-floating stellar remnants such as white dwarfs, neutron stars, and black holes can produce microlensing events. These objects may originate from stellar evolution rather than planet formation, but their detection helps map the population of compact objects. A microlensing event caused by a black hole would have a long timescale and produce no light from the lens. Distinguishing such events from massive planets involves careful analysis and, where possible, astrometric measurements. Thus, microlensing surveys contribute to our understanding of stellar death as well as planetary birth. The gravitational field of a star cluster could, in theory, lens background light. While the collective effect of many stars is weak, the overall cluster mass can slightly magnify or shear background images. Similarly, a dense population of rogue planets in a region might produce a statistical microlensing signal, subtly altering the brightness distribution of distant stars. Detecting such a background effect would require precise measurements and could reveal the cumulative mass of unseen objects, linking microlensing to studies of dark matter and cosmic structure. On the theoretical front, models of gravitational scattering predict that interactions among three or more bodies can lead to chaotic outcomes. When a planet experiences close encounters with two giant planets, it may gain enough energy to escape the system entirely. The probability of ejection depends on the masses and separations of the bodies involved, and on the timing of resonances. Statistical studies of planetary systems suggest that multi-planet architectures with several giants are more likely to produce rogues. These predictions can be tested as the census reveals the masses of free-floating planets. Some planetary systems may undergo a different evolutionary path, where orbital migration brings a giant planet close to its star, creating a hot Jupiter. In the process, smaller planets can be destabilized and ejected. The remaining system may consist of a single close-in giant and a depleted outer region. Observing a correlation between the presence of hot Jupiters and the frequency of rogues in a stellar neighborhood could hint at shared origins. This connection between different exoplanet types underscores the interconnectedness of planetary system dynamics. The connection between microlensing and other astrophysical phenomena extends to gravitational waves. When compact objects collide or orbit, they produce ripples in spacetime that can be detected by gravitational wave observatories. A population of free-floating black holes or neutron stars may contribute to gravitational wave signals. Conversely, gravitational wave detections can inform microlensing surveys about the abundance of compact objects. The interplay between these disciplines demonstrates how multiple lines of evidence converge to reveal the invisible components of the universe. Microlensing can also occur at different wavelengths, from optical to radio. Radio microlensing has been proposed for detecting compact objects that lens radio-bright quasars. Similarly, infrared microlensing could be used to detect lensing of luminous infrared sources by cold objects. Each wavelength range offers different advantages and challenges, such as sensitivity to dust or source size. Exploring microlensing across the spectrum broadens the range of detectable lenses and complements optical surveys. Spectral variations during a microlensing event provide an additional diagnostic. If the source star has spots or other surface features, the magnification of different parts of the star during the lensing event can cause spectral lines to shift. This effect, known as chromatic microlensing, has been used to study the atmospheres of distant stars. In the context of rogue planet detection, chromaticity could potentially reveal subtle differences between lensing by planets and by other compact objects. Such multi-wavelength approaches promise richer datasets and deeper insights. The gravitational focusing of cosmic rays and neutrinos by rogue planets is an exotic but intriguing possibility. Just as light is bent, so too are trajectories of charged particles and neutrinos in gravitational fields, though the effect is tiny. In principle, a massive rogue planet passing in front of a distant cosmic source could slightly modulate the flux of high-energy particles. Detecting such effects is far beyond current capabilities, but considering them highlights the universality of gravitational lensing across physical phenomena. Beyond microlensing, other detection methods may reveal rogue planets. Astrometry, the precise measurement of a star's position on the sky, can detect the tiny wobble caused by a planet's gravitational pull. If a star suddenly acquires a distant companion through capture, its trajectory may show an unexplained deviation. Likewise, the transit method could, in rare cases, detect a rogue planet passing in front of a background star, producing a brief dip in brightness. Combining astrometric, transit, and microlensing data may increase confidence in identifying rogue planets and constrain their properties. Infrared surveys, searching for faint, cold objects, may directly image nearby free-floating planets. These surveys look for red, self-luminous objects moving against the background. Advances in detector sensitivity and adaptive optics have enabled the discovery of very low-mass, brown dwarfs and planetary mass objects in star-forming regions. Finding such objects in the field, far from any star, confirms that some rogues can be directly detected without lensing. The synergy between imaging and microlensing provides cross-validation of the rogue population. Space telescopes specializing in infrared wavelengths, such as those currently in operation, have revolutionized our view of star-forming regions. Their ability to see through dust reveals clusters of protostars, brown dwarfs, and planetary mass objects. Observations have uncovered filaments of gas and dust, where stars and rogue planets may form side by side. The presence of free-floating planetary mass objects in these regions supports the idea that star-like fragmentation can produce objects with planetary masses, a key point in the origin debate. The detection of disks around free-floating planets calls for a closer examination of disk physics. Protoplanetary disks around stars show a rich interplay between gas and dust, with processes such as accretion, turbulence, and planet formation shaping their evolution. Scaling down the mass and luminosity introduces new dynamics. Disks around rogue planets are cooler and less massive, yet they may still support the formation of moons or minor planets. Studying these disks can reveal how universal disk processes are across different central object masses. If moons form around free-floating giants, they may undergo tidal interactions that heat their interiors. These interactions depend on the moon's orbital eccentricity and the planet's mass. In a starless environment, the system's evolution is driven solely by internal dynamics, free from external tides. Modeling these interactions can predict whether moons maintain subsurface oceans, become tidally locked, or migrate outward over time. Observationally, detecting moons around free-floating planets remains beyond current capabilities, but future instruments could search for faint periodic signals indicative of satellites. The existence of rogue planets invites us to consider the concept of planetary boundaries. On Earth, boundaries between land and ocean, or atmosphere and space, define regions of exchange. A free-floating planet has boundaries defined by gravity and magnetism, but beyond that, it interfaces directly with the interstellar medium. Charged particles and dust interact with its magnetosphere. Cosmic rays bombard its atmosphere. The planet's journey through varying interstellar environments may influence its atmospheric chemistry and surface conditions. Understanding these interactions adds another layer to the study of planetary atmospheres. From a cosmological perspective, the density of rogue planets could affect the dynamics of galaxies. Although individual planets are small, their collective mass might contribute to the baryonic mass budget of galaxies. In regions with high rogue planet density, their gravitational effects could slightly alter the rotation curves or the collapse of gas clouds. While these effects are likely minor compared to stars and dark matter, they illustrate the interconnectedness of cosmic structures. Quantifying the total mass in rogue planets helps complete the inventory of matter in the universe. As we contemplate such cosmic inventories, we recognize that the classification of matter extends beyond baryons to include dark matter and dark energy. Free-floating planets exist within this broader context, interacting gravitationally with both visible and invisible components. Their distribution may trace underlying gravitational potentials shaped by dark matter halos. Microlensing surveys could, in principle, detect dark matter clumps if they produce lensing events. Thus, the search for rogue planets intersects with the search for the unseen majority of the universe. In the far future, as humanity advances technologically, the prospect of visiting a rogue planet becomes less fanciful. Interstellar probes, equipped with nuclear or fusion propulsion, could reach a nearby rogue in a time span of decades. Such a mission would provide direct measurements of mass, atmosphere, magnetism, and geology. The scientific return would be immense, offering insights into planetary physics under conditions not found in the solar system. Preparing for such missions begins now, with the identification and characterization of candidate targets through observations and surveys. Ethical considerations also arise when contemplating the exploration or exploitation of rogue planets. These worlds may harbor unique ecosystems or resources. Decisions about whether to alter them, extract materials, or settle on them involve ethical frameworks that balance scientific curiosity, preservation, and potential benefit. Engaging with ethicists and policymakers early in the planning stages of future missions will help ensure that exploration proceeds responsibly and in alignment with international consensus. Finally, the human fascination with lonely worlds ties into broader themes of identity and belonging. Stories of rogue planets resonate with feelings of solitude and resilience, reflecting the human condition. The knowledge that such worlds exist expands our sense of home beyond the solar system. It invites us to imagine the experiences of hypothetical inhabitants, to empathize with the notion of isolation, and to celebrate the universal drive to seek understanding and connection. In this way, science and storytelling intertwine, enriching our appreciation of both the universe and ourselves. As we approach the next stage of our exploration, the narrative remains open-ended. The possibilities are vast. New telescopes may reveal thousands of rogues. New models may rewrite our understanding of their origins. And new stories may emerge from their discovery. Each question answered gives rise to more, and each new detection adds a point of light to the map of the unseen. With patience, curiosity, and collaboration, the journey will continue, inviting us deeper into the mystery of planets adrift in interstellar space.